There's something deeply humbling about staring up at the night sky and realizing just how little we truly understand. The universe is an endless tapestry of wonder, filled with phenomena so bizarre, so utterly inexplicable, that even the brightest minds in science are left scratching their heads. Think about that for a moment. In an age where we've mapped the human genome, split the atom, and sent probes beyond our solar system, there are still cosmic mysteries that defy every explanation we throw at them. And that's exactly what makes them so thrilling. Imagine, if you will, a galaxy where stars vanish without a trace, black holes that shouldn't exist, or cosmic explosions with no apparent cause. These aren't plot points from a sci-fi novel, they're real, documented events happening right now in the depths of space. And today, we're diving headfirst into 50 of the most mind-bending, spine-tingling enigmas the universe has to offer. From rogue planets drifting through the void to signals from deep space that repeat like clockwork, each one of these phenomena challenges everything we think we know about the cosmos. This isn't just a list, it's an invitation to explore the very edges of human understanding. Because here's the thing, every unexplained mystery is a doorway, a chance to question, to wonder, and maybe even to discover something groundbreaking. Whether you're a seasoned space enthusiast or someone who just loves a good cosmic puzzle, there's something here that'll make you pause and stare at the stars a little differently. So buckle up. We're about to venture into the strangest, most awe-inspiring corners of the universe where the rules of physics seem to bend and the answers are still waiting to be found. It was just an ordinary evening in Ohio on August 15, 1977, when astronomer Jerry Amon was scanning the skies for signs of intelligent life. The Big Ear radio telescope at Ohio State University was methodically listening to the cosmos, sifting through the static for anything unusual, until suddenly, it wasn't static at all. For 72 seconds, a powerful, narrowband radio signal blasted through the receiver at exactly 1,420 MHz, a frequency scientists call the water hole, because it sits between hydrogen and hydroxyl radio waves, the perfect channel for interstellar communication. The signal was so strong, so deliberately focused, that when Amon reviewed the data printout, he circled the sequence in red pen and scribbled, "Wow." In the margin, that single word gave the phenomenon its name and its legend. Here's what makes the wow signal so haunting. It wasn't random noise, it matched every criterion scientists had predicted for an artificial transmission. It came from the direction of the constellation Sagittarius, where no human satellites or known cosmic events could explain it. And then, just as abruptly as it appeared, it vanished. Despite decades of follow-up searches, including repeated scans by more advanced telescopes, the signal never repeated. No natural phenomenon, no pulsar, no quasar, no passing comet has ever convincingly explained it. Even Amon himself spent years trying to debunk his own discovery, ruling out everything from military transmissions to reflections off space debris. The WOW signal remains a cosmic one-hit wonder, a tantalizing whisper from the void that raises more questions than answers. Could it have been a fleeting hello from an advanced civilization? A glitch in our own technology, or something even stranger we haven't considered? The silence since then is as eerie as the signal itself. If it was aliens, why didn't they call back? If it wasn't, how did nature produce a signal so perfectly engineered to catch our attention? One thing's certain, in a universe that's mostly quiet, the WOW signal is a scream we still can't ignore. If the WOW signal left us wondering who or what might be out there, dark matter presents an even deeper cosmic riddle. It's the universe's most frustrating magic trick. All around us, something invisible is pulling the strings, shaping galaxies, bending light, and holding the cosmos together. Yet no matter how hard we look, we can't see it, touch it, or even figure out what it truly is. The numbers alone are staggering. Dark matter makes up roughly 27% of everything in existence, while the ordinary matter we know, the stuff of stars and planets and you and me, accounts for less than 5%. The rest, that's another mystery entirely. The clues started piling up back in the 1930s when astronomer Fritz Zwicky noticed something odd about the Coma galaxy cluster. The galaxies were moving so fast that by all rights they should have flown apart unless there was some unseen mass holding them together with gravity. Decades later, Vera Rubin's observations of spinning galaxies confirmed it. Stars at the edges were whirling just as fast as those near the center, defying the laws of motion unless an invisible halo of matter was keeping them in check. Every shred of evidence points to the same conclusion: dark matter is real and it's everywhere, but what is it made of? Scientists have their best guesses. Leading theories suggest weakly interacting massive particles, or WIMP hypothetical particles that barely interact with normal matter except through gravity. Underground labs hunt for them in ultra-sensitive detectors shielded from cosmic rays, while particle colliders like the Large Hadron Collider try to create them in high-energy crashes. Others propose actions, ultralight particles streaming through space like an invisible mist, but so far every experiment has come up empty. Even stranger, some researchers wonder if we've been wrong all along. Maybe dark matter isn't a particle at all, but a sign that gravity itself works differently on cosmic scales. The frustration is palpable. Dark matter's fingerprints are all over the universe, from the way galaxies cluster together to the gravitational lensing that warps distant starlight. Yet after nearly a century of searching, it remains a ghost in the cosmic machinery, a silent partner in the dance of the cosmos, felt but never seen. Every failed detection only deepens the mystery, leaving us to grapple with a humbling truth. The universe is far stranger than we imagined, and some of its greatest secrets are still hiding in plain sight. If dark matter is the universe's invisible scaffolding holding galaxies together in a cosmic embrace, dark energy is something far more unsettling, a force that's actively tearing the fabric of reality apart. Picture this: not only is the universe expanding, but that expansion is accelerating, as if some unseen hand is pressing harder on the gas pedal with every passing second. Scientists discovered this shocking reality in the late 1990s while studying distant supernova, expecting to find the expansion slowing down under gravity's pull. Instead, they found the opposite: space itself was stretching faster and faster, as though repelled by a mysterious energy woven into the void. This is where dark energy enters the stage, a phenomenon so baffling it makes dark matter seem almost straightforward. While dark matter tugs things together with gravity, dark energy pushes them apart with what can only be described as anti-gravity. It accounts for a staggering 68% of the universe's total energy, dwarfing both dark and ordinary matter combined. The implications are staggering. If this acceleration continues unchecked, galaxies will eventually vanish over the cosmic horizon, their light unable to reach us, leaving the night sky an empty abyss. But what is dark energy? The leading explanation harks back to an idea Einstein once called his greatest blunder: the cosmological constant, a term he added to his equations to keep the universe static. When the expansion of the universe was later confirmed, he discarded it. Yet now, it's back in vogue as a candidate for dark energy, a uniform energy density inherent to space itself, causing it to repel rather than attract. But there's a problem. Quantum physics predicts this energy should be many orders of magnitude stronger than what we observe, leaving scientists scrambling for other explanations. Some propose an even wilder notion: dark energy isn't constant at all, but a dynamic field that could change over time, dubbed quintessence. Others wonder if we're seeing the effects of extra dimensions or flaws in Einstein's theory of gravity itself. The truth is, we're grasping at shadows, trying to define something that might forever lie beyond our comprehension. What's certain is that dark energy holds the keys to the universe's ultimate fate, whether it will end in a big rip, a slow fade to black, or something stranger still. Every observation deepens the mystery. The James Webb Space Telescope, for instance, recently found galaxies from the early universe that appear too mature for their age, hinting that dark energy's influence might have changed over cosmic time. It's a humbling reminder. Just when we think we're close to unlocking the universe's secrets, it throws us a curveball, leaving us to wonder what else is out there, silently shaping the destiny of everything we know. In the vast ocean of stars, one particular flickering light has captured imaginations like no other. KIC 8462852, better known as Tabby's star. Named after astronomer Tabitha Boyajian, who first brought its bizarre behavior to the world's attention in 2015, this unassuming star in the constellation Cygnus doesn't play by the rules. Most stars dim slightly and predictably when planets pass in front of them like clockwork. But Tabby's star, it's more like a cosmic strobe light, plunging in brightness by as much as 22% at irregular intervals, sometimes for days, sometimes for weeks, with no clear rhythm or reason. At first, even the most cautious scientists couldn't help but entertain the wildest possibility. Could this be evidence of alien technology? The idea wasn't entirely far-fetched. In the 1960s, physicist Freeman Dyson had theorized that an advanced civilization might build vast solar collectors megastructures encircling a star to harness its energy. Tabby's star's erratic dimming seemed to fit the bill. Imagine a swarm of artificial constructs blotting out the star's light as they orbit in some incomprehensible pattern. The hypothesis sent ripples through the astronomy community and beyond, sparking headlines and hopeful speculation. But science thrives on skepticism, and over time, alternative explanations emerged. Detailed spectral analysis revealed something unexpected. The dimming wasn't uniform. If solid megastructures were blocking the light, they'd leave sharp, distinct shadows. Instead, the data showed a smeared, uneven dimming, more consistent with clouds of fine dust particles drifting around the star. Some researchers proposed swarms of comets or fragments from a shattered planet, while others pointed to the star's own erratic behavior, like massive stellar flares or magnetic activity unlike anything we've seen before. The truth is, Tabby's star defies every model we have. Young stars can be unpredictable, but this one appears middle-aged. Dust clouds might explain some dimming, but they don't account for historical observations dating back to the 19th century, which suggest the star has been fading gradually for over a century. Even the most conservative estimates admit this isn't just an oddball. It's a cosmic anomaly that challenges our understanding of how stars live, age, and interact with their surroundings. What makes Tabby's star so compelling isn't just the lingering question of what's causing its dimming, it's the reminder that the universe is still full of surprises. For every alien megastructure fantasy, there's a deeper, stranger reality waiting to be uncovered. Whether it's dust, debris, or something beyond our current theories, one thing's certain: this star isn't done keeping us guessing. Imagine a pulse of radio waves so powerful it outshines an entire galaxy, but only for a fraction of a second. No warning, no afterglow, just a blinding cosmic flash vanishing as quickly as it appeared. This isn't science fiction. It's the bizarre reality of fast radio bursts, or FRB, some of the most enigmatic signals ever detected in the universe. First discovered in 2007, these fleeting blasts of energy last mere milliseconds, yet pack more punch than 500 million suns. What's truly unsettling? We still don't know what's creating them. The mystery took an even stranger turn in 2016 when astronomers spotted something unprecedented, an FRB that repeated. Dubbed FRB 121102, this signal erupted from the same patch of sky over and over, defying the one-and-done behavior of its predecessors. Suddenly, the leading theories, cataclysmic explosions, evaporating black holes, or neutron stars collapsing, needed rethinking. If FRBs were supposed to be the death throes of cosmic objects, how could one keep firing like a celestial machine gun? Possible explanations range from the mundane to the extraordinary. Some point to highly magnetized neutron stars called magnetars, whose crust-quaking starquakes could release torrents of radio waves. Others suggest collisions between dense objects like white dwarfs or black holes, though these events should be rare, hardly matching the rate at which FRBs flood the cosmos. Then there's the wild card: could some FRBs be artificial? The repeating bursts, with their precise frequencies and patterns, have fueled speculation about advanced civilizations harnessing unimaginable energy. But before you jump to alien transmitters, consider this: nature often outdoes our wildest imaginations without needing a technological explanation. The plot thickened when scientists traced one FRB to a surprising source: a spiral galaxy not unlike our own Milky Way, home to a modest magnetar. It was a tantalizing clue, yet for every burst we've localized, dozens remain untraceable, scattered across the sky like cosmic breadcrumbs, leading to answers just out of reach. The real challenge: catching them in the act. FRBs are so brief that by the time telescopes swing toward their origin, they're already gone. What keeps astronomers awake at night isn't just the what or the how, it's the sheer scale of the phenomenon. Current estimates suggest an FRB occurs somewhere in the universe roughly every second. That's a symphony of invisible flashes playing non-stop, each one a potential key to understanding extreme physics, the structure of the cosmos, or even phenomena we haven't dreamed up yet. Whether they're cosmic lighthouses, space-time ripples, or something beyond our current science, FRBs remind us that the universe is far from quiet. It's shouting secrets we're only beginning to hear. Deep in the constellation Centaurus, something massive is pulling us, and everything around us toward it at over 14 million miles per hour. Astronomers call it the Great Attractor, a gravitational behemoth so powerful it bends the paths of entire galaxies like leaves caught in a cosmic river. Here's the frustrating part: we can't actually see it. Our own galaxy's dense disk of stars, gas, and dust, the so-called zone of avoidance, blocks our view like a celestial curtain, leaving this mysterious force hidden in plain sight. The first clues emerged in the 1970s when astronomers mapping the universe's large-scale structure noticed something odd. Galaxies within our local supercluster, including the Milky Way, weren't just drifting apart as space expanded, they were all streaming toward the same invisible point. The sheer scale of this motion defied explanation. Whatever lay in that direction had to be unimaginably massive, with the gravitational pull of tens of thousands of Milky Ways combined. Yet telescopic surveys revealed nothing obvious, just a void obscured by the Milky Way's glare. Breaking through the zone of avoidance required ingenuity. Infrared and radio telescopes, which peer through dust clouds, began piecing together fragments of the puzzle. What they found only deepened the mystery. Behind the veil lies the Norma cluster, a dense gathering of galaxies anchored by a colossal galaxy dubbed Able 3627. But here's the catch: even this megacluster isn't nearly heavy enough to account for the Great Attractor's pull. So what's really out there? Some theorists argue we're seeing the fingerprints of an even larger structure, perhaps the core of the Laniakea supercluster, a vast cosmic web where galaxies flow like tributaries toward a central gravitational basin. Others propose dark matter's uneven distribution could be amplifying the effect, creating a sort of gravity well on a scale we've never measured. Then there's the wild card: could the Great Attractor itself be moving, tugged by something else beyond our horizon, like the even more massive Shapley supercluster? The stakes are higher than just solving a cosmic whodunit. Understanding the Great Attractor reshapes our place in the universe. We're not just passive observers, we're participants in a grand gravitational dance, swept along by forces we're only beginning to map. Every new observation peels back another layer, revealing how much we don't know about the invisible scaffolding shaping everything around us. One day, with more advanced telescopes or even interstellar probes, we might finally stare this giant in the face. Until then, it remains a humbling reminder. Sometimes the universe's most powerful forces are the ones we can't see. Galaxies might seem like peaceful islands of light in the cosmic dark, but the truth is far more violent. They're predators. Take Andromeda, our closest galactic neighbor, a stunning spiral that's also a relentless devourer of dwarf galaxies. Hubble's sharp eye has caught it red-handed, with ghostly streams of stars stretching across space like cosmic crumbs from a half-finished meal. These are tidal streams, the shredded remains of smaller galaxies that wandered too close, torn apart by Andromeda's immense gravity until nothing was left but these shimmering trails. And here's the unsettling part: our own Milky Way might be just as guilty. Astronomers call it galactic cannibalism, and it's how the biggest galaxies grow. Gravity doesn't play favorites. When a small galaxy drifts near a larger one, the tidal forces stretch it like taffy, pulling stars away in long arcs. Some get swallowed whole, others are ripped into stellar spaghetti. The evidence is everywhere once you know where to look. In the Milky Way's halo, ancient star clusters and oddball stars moving against the galactic flow hint at past feasts. One victim, dubbed the Gaia sausage, is thought to be the remains of a dwarf galaxy that collided with us 10 billion years ago, its stars now scattered through our galaxy like fossils. What's chilling is how routine this destruction seems. The universe is full of these cosmic crime scenes. The Canis Major Dwarf Galaxy, for instance, is currently being absorbed by the Milky Way, its stars strewn along a looping ribbon visible in infrared. Meanwhile, the Large Magellanic Cloud, a satellite galaxy once thought to be orbiting peacefully, is now known to have its own warped shape, likely from a past encounter with our galaxy's hunger. Andromeda's appetite offers a glimpse of our future. In 4 billion years, it's set to collide with the Milky Way in the ultimate act of galactic cannibalism. The two spirals will merge, their stars flung into new orbits, their gas compressed into bursts of new star formation. A fiery dance that will erase the familiar sky forever. Yet even this cataclysm is just part of the cycle. Galaxies grow by consuming others, building themselves up from the wreckage of their neighbors. It's a humbling thought. The beauty of a spiral arm, the glow of a galactic center, might just be the aftermath of an ancient, invisible feast. Perhaps the most haunting question isn't which galaxies we've eaten. It's what scars we've yet to find. With every deeper sky survey, new tidal streams emerge, each one a silent witness to the universe's quiet, relentless violence. The night sky might look serene, but behind the glittering curtain, it's a battlefield, and we're standing right in the middle of it. Imagine a hole punched through the universe, not a black hole's crushing darkness, but a vast, echoing emptiness where galaxies should be. That's the Boötes Void, a spherical chasm stretching 330 million light-years across, so barren that astronomers call it the Great Nothing. To put that in perspective, if the Milky Way sat at its center, we wouldn't have discovered another galaxy until the 1960s. This isn't just a sparse region. It's a cosmic desert so extreme it defies every model of how the universe structures itself. The Void's discovery in the 1980s sent shockwaves through cosmology. While the universe has plenty of gaps, bubbles, and tunnels woven into the cosmic web, Boötes is an outlier. On average, a space that size should contain around 2,000 galaxies. Instead, it holds a mere 60, scattered like lonely outposts in an endless wasteland. The few galaxies that do cling to existence there are oddly isolated, with none of the usual clusters or satellite galaxies tagging along. It's as if someone took a cosmic eraser and scrubbed away nearly everything in this region of space. So what could carve such a void? One theory points to inflation, the rapid expansion of the universe moments after the Big Bang. tiny quantum fluctuations during that period might have stretched into vast underdensities, leaving behind these eerie blanks. Another idea suggests the void isn't empty at all, just filled with something we can't see, like an absurdly large concentration of dark matter, warping space so severely that normal galaxies never formed. Then there's the wild card. Could it be evidence of a collision with another universe? Some models of multiverse theory predict such collisions might leave scars in our cosmos, regions where matter was somehow pushed aside. But here's the twist: Boötes might not be as empty as we thought. Recent surveys hint at faint dwarf galaxies lurking in the void, too dim for earlier telescopes to spot. If confirmed, it could mean the void isn't a total anomaly, just an extreme example of how matter clusters unevenly. Yet even this explanation feels unsatisfying. The scale is still too vast, the gap too profound. It's like finding a single grain of sand in an Olympic-sized swimming pool and calling it crowded. What makes the Boötes void so unsettling isn't just its emptiness, it's the lingering question of whether we're missing something fundamental about how the universe works. Every time we think we've mapped the limits of cosmic structure, places like this remind us how much remains hidden. Perhaps the void is a statistical fluke, a 1 in a trillion accident. Or perhaps it's a signpost pointing toward physics we haven't yet imagined. Either way, it's a humbling glimpse into how little we truly understand about the grand tapestry of existence. Rising from the heart of our galaxy like twin cosmic geysers, the Fermi Bubbles stretch 25,000 light-years above and below the Milky Way's disk, a pair of colossal structures glowing with high-energy gamma rays. Discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope, these gargantuan lobes left astronomers stunned. Here's the puzzle: they're not made of stars, gas, or anything visible. Instead, they're vast, faint shells of something far more exotic, crackling with particles moving at nearly the speed of light. And their origin, that's where the mystery deepens. One leading theory points to the supermassive black hole at our galaxy's center, Sagittarius A. While it's quiet today, astronomers suspect it wasn't always so well behaved. Around 4 million years ago, it might have gorged itself on a massive cloud of gas or even a star, triggering a cataclysmic eruption. The energy released could have blasted jets of material outward, inflating these bubbles like cosmic balloons. We've seen similar outbursts in distant galaxies, proof that black holes can indeed throw tantrums of cosmic proportions. But here's the catch: the Fermi Bubbles' edges are too sharp, too well-defined for a chaotic explosion. It's as if they were sculpted by something far more precise. That's where dark matter enters the scene. Some researchers propose these bubbles are evidence of dark matter particles annihilating each other near the galactic center, releasing bursts of gamma rays in the process. It's a tantalizing idea. Dark matter is thought to cluster densely around black holes, and if particles collided there, they might leave behind exactly this kind of high-energy fingerprint. Yet skeptics argue the signal doesn't quite match predictions. If it's dark matter, why don't we see similar bubbles elsewhere? The debate gets even stranger when you consider the bubble's relationship with another Milky Way enigma, the so-called Rosetta bubbles. These X-ray structures, discovered in 2020, overlap with the Fermi Bubbles but extend even farther, suggesting multiple violent events might have shaped our galaxy's core. Could this be evidence of cyclical black hole eruptions, like a heartbeat pulsing every few million years? Or is there an entirely different engine powering these phenomena, something we haven't even theorized yet? What makes the Fermi Bubbles so captivating isn't just their scale or their eerie glow. It's the realization that even our home galaxy harbors secrets we've barely begun to decode. They're a reminder that the cosmos doesn't just hold mysteries in distant realms. Sometimes the most profound puzzles are right over our heads, hidden in plain sight. Whether forged by black hole fury or dark matter's invisible hand, these bubbles whisper a tantalizing question: What other invisible giants might be lurking in the sky, waiting to be discovered? Black holes were supposed to be the universe's ultimate vaults, cosmic prisons where anything that crossed the event horizon vanished forever, its information locked away from the rest of reality. Then Stephen Hawking turned that idea on its head. In 1974, he made a startling prediction: black holes aren't eternal. They slowly leak energy, emitting what we now call Hawking radiation, a faint glow of particles born from quantum fluctuations near the event horizon. Over unimaginable eons, this process causes black holes to evaporate, shrinking until they finally pop out of existence. But here's the catch: Hawking's math suggested the radiation carried no information about what fell in. If true, it meant the universe had a glaring loophole. Information could be permanently erased, violating a bedrock principle of quantum mechanics that states information must always be preserved. This became the black hole information paradox, a battle between two pillars of physics. On one side, quantum mechanics insists information can't vanish. It might be scrambled but never destroyed. On the other, general relativity says black holes swallow everything indiscriminately, leaving no trace behind. For decades, physicists wrestled with this contradiction, sparking debates so heated they've been called the black hole wars. The stakes: if Hawking was right, we'd need to rewrite the laws of quantum physics. If he was wrong, Einstein's theory of gravity might need an overhaul. Then came the firewall proposal, a radical idea suggesting the event horizon isn't the smooth gateway relativity describes, but a searing wall of high-energy particles that obliterates anything crossing it. Picture falling toward a black hole, expecting to glide seamlessly into the abyss, only to hit an invisible barrier hotter than a supernova. The firewall would preserve information by burning it into the radiation, but at a cost. It shatters our classical view of black holes. Critics argue this violates Einstein's equivalence principle, which states free-falling observers shouldn't notice anything unusual at the event horizon. Recent breakthroughs hint at a middle ground. The holographic principle suggests information isn't lost, it's smeared across the black hole's surface like a cosmic hologram, encoded in ways we're just beginning to decipher. Meanwhile, calculations in string theory show Hawking radiation might indeed carry subtle fingerprints of what fell in, solving the paradox without firewalls or broken physics. But the mystery isn't settled. Some theorists propose black holes never fully evaporate, leaving behind microscopic remnants packed with compressed information. Others wonder if the paradox is a sign we're missing a deeper theory that unites gravity and quantum mechanics. What makes this debate so thrilling isn't just the fate of hypothetical falling astronauts or the math on a chalkboard. It's the realization that black holes might be the universe's most profound teachers. They're not just objects, they're puzzles forcing us to confront the limits of our understanding. Every proposed solution peels back another layer, revealing how much we still have to learn about the fabric of reality itself. Whether through holograms, firewalls, or something stranger, one thing's certain: the answer won't just rewrite textbooks, it could redefine how we see the cosmos. When NASA's twin Pioneer probes launched in the 1970s, they were designed to push the boundaries of exploration, first to Jupiter and Saturn, then beyond our solar system into the unknown. But as they ventured farther from Earth, something bizarre happened. Both spacecraft began slowing down ever so slightly, as if an invisible hand were tugging them backward. This tiny deceleration, just a fraction of what gravity alone could explain, became known as the Pioneer anomaly, and for decades it haunted physicists like an unsolved equation scribbled in the margins of the universe's textbook. At first glance, the numbers didn't make sense. The probes were drifting toward the outer solar system, yet their trajectories showed a persistent, unmodeled drift toward the Sun, a deviation so small it amounted to just 300 miles over a decade, but consistent enough to defy coincidence. Scientists ran through every conceivable explanation: gravitational pull from unseen objects, glitches in onboard systems, even the drag of interstellar dust. None fit, the anomaly lingered like a ghost in the data, sparking wilder theories. Could it be a sign of modified gravity challenging Einstein's relativity? Or evidence of dark matter's subtle influence on our cosmic neighborhood? Then came a breakthrough, one that seemed almost too mundane for such a cosmic mystery. In 2012, a team meticulously reconstructed the probe's heat signatures and realized the answer had been radiating away all along. The Pioneer's nuclear power sources generated heat, which bounced off their asymmetrical structures, creating a tiny but constant push away from the Sun. Since the spacecraft was stabilized by spinning, this thermal recoil acted like a minuscule thruster, subtly altering their speed. Case closed, not quite. While the thermal explanation fits most of the data, a stubborn few discrepancies remain. Some researchers argue the math doesn't fully account for the observed drift, leaving the door cracked open for alternative ideas. Could there be an undiscovered gravitational quirk at the solar system's edge? Or does the anomaly hint at some deeper, unseen interaction between matter and energy? Even now, the debate simmers, a reminder that sometimes the smallest mysteries, like a faint whisper of heat in the void, can echo the loudest questions about how the universe really works. What makes the Pioneer anomaly so enduring isn't just the puzzle itself, but what it represents, the humbling reality that even our most precise instruments can stumble upon the unexpected. Whether solved or still half hidden, it's a testament to the fact that exploration doesn't just reveal answers, it keeps us asking better questions. The cosmic microwave background radiation is supposed to be the universe's most impartial witness, a relic of the Big Bang that blankets the cosmos in near-perfect uniformity, whispering secrets about the infancy of everything we know. But in 2003, cosmologists poring over data from NASA's Wilkinson microwave anisotropy probe stumbled upon something so unsettling they dubbed it the axis of evil. Stretching across the sky like a phantom spine, this controversial alignment connects unexpected hotspots in the CMB with our own solar system's orientation, as if the universe were playing favorites with Earth. At its core, the finding violates one of cosmology's most sacred principles, isotropy, the idea that the universe should look roughly the same in all directions, no matter where you're standing. Yet here was evidence that the CMB's fluctuations, tiny temperature variations encoding the seeds of galaxies, weren't entirely random. Instead, they appeared loosely aligned with the plane of our solar system, an eerie coincidence that defied odds calculated at less than 1 in 1,000. Skeptics scrambled to dismiss it as a statistical fluke or measurement error, but subsequent observations, including data from the Planck satellite, only deepened the mystery. The axis persisted, stubborn as a fingerprint on the cosmic window. The implications are profound. If the universe isn't as isotropic as we thought, it could upend models of cosmic inflation. The theory that the early universe expanded faster than light, smoothing out irregularities. Some theorists propose wild explanations, like pre-Big Bang structures imprinting patterns on space-time, or our universe brushing against another in a hidden dimension. Others suggest more mundane culprits, perhaps foreground interference from galactic dust or subtle instrumental biases are warping our view. But so far, no correction fully erases the axis. What truly unsettles scientists isn't just the alignment, it's the creeping suspicion that we might be seeing a cosmic illusion, a trick of perspective that hints at deeper layers of reality. Could there be structures so vast they curve space-time on scales we've never measured? Or does the axis of evil expose a flaw in our assumptions about the universe's fundamental fairness? Every unanswered question tightens the knot. The more we study the cosmos, the more it seems to gaze back at us as if we're part of the experiment. This isn't just a puzzle about the early universe, it's a mirror, forcing us to confront how much we still don't know about our place in the grand scheme of things. The moon shouldn't have a magnetic field, at least, not according to everything we know about how planets work. With a core just 1% the size of Earth's, our lunar companion lacks the churning molten metal that generates our planet's protective magnetic shield. Yet when Apollo astronauts brought back moon rocks in the 1960s and 70s, they carried a shocking secret. These ancient stones were magnetized as if bathed in a powerful magnetic field billions of years ago. The discovery sent scientists scrambling. How could a world so small, so geologically quiet, once have possessed a magnetic field rivaling Earth's, and where did it go? One leading theory points to a lunar dynamo, a molten, spinning core that once generated a magnetic field, much like Earth's does today. But here's the puzzle. Dynamos require both heat and motion, and the moon's tiny core should have cooled and solidified eons ago. Computer simulations suggest a possible solution. In the moon's youth, its orbit was much closer to Earth, and the gravitational tug of war between the two bodies might have kept the lunar core churning like a cosmic blender. This orbital energy could have powered a dynamo for 1 billion years before the moon drifted away and the engine sputtered out. There's just one problem. Some magnetized rocks are younger than this timeline, hinting the field lingered longer than physics should allow. Enter the impact hypothesis. The moon's surface is a graveyard of colossal collisions, and some researchers argue these cataclysms could have temporarily jump-started a magnetic field. How, when a massive asteroid strikes, it doesn't just leave a crater, it sends shockwaves through the lunar interior, potentially stirring the core like a spoon in coffee. Simulations show such trauma might briefly reactivate a dynamo, imprinting magnetism into freshly formed rocks before fading again. The idea gains traction from the fact that many magnetized samples come from regions scarred by ancient impacts. But skeptics counter that even the biggest strikes wouldn't pack enough energy to explain the field's inferred strength. Then there's the wild card, plasma spheres. Some theorists propose that the young moon was shrouded in a temporary magnetic bubble created by Earth's own magnetosphere. As our planet's field lines stretched and twisted, they might have enveloped the moon, bathing it in a borrowed magnetic field strong enough to magnetize surface rocks. It's an elegant fix, except that lunar samples show directions of magnetization that don't always align with Earth's historical field, suggesting something more complex was at play. What makes this mystery so gripping isn't just the scientific tug of war, it's the stakes. If the moon once had a robust magnetic field, it might have sheltered a temporary atmosphere, shielding water ice in permanently shadowed craters from solar wind. That reshapes our understanding of the moon as a static, airless wasteland, hinting at a more dynamic past where conditions might have even briefly flirted with habitability. Every rock, every crater, every subtle magnetic whisper is a clue to a lunar history far stranger than we ever imagined. And with new missions like Artemis poised to return to the moon with modern instruments, we might finally be on the verge of cracking a puzzle that's lingered since the Apollo era, proving once again that even our closest celestial neighbor hides secrets waiting to rewrite the textbooks. Looming over Saturn's north pole like a colossal cosmic stop sign, the Saturn hexagon is one of the most precisely geometric storms ever discovered in our solar system. This six-sided jet stream, wider than 2 Earths stacked side by side, has churned relentlessly for at least 4 decades, possibly much longer, defying every expectation of how planetary atmospheres behave. Unlike the chaotic hurricane spirals we see on Jupiter or Earth, this structure is unnervingly symmetrical, its razor-sharp angles maintained with almost mathematical precision as it rotates. The question isn't just how such a shape forms, it's how anything in nature could sustain such perfect geometry on this mind-bending scale. To crack this puzzle, scientists turn to one of the most unpredictable forces in physics, fluid dynamics. In labs on Earth, researchers have recreated miniature versions of the hexagon by spinning tanks of liquid at carefully controlled speeds, the key ingredient. sheer layers of fluid moving at different velocities. When conditions are just right, the interplay between these layers can generate stable polygonal shapes, including hexagons, as faster-moving streams carve geometric edges into slower ones. It's like stirring a cup of tea and watching honey swirl into hexagons instead of circles, a phenomenon that shouldn't happen unless the forces involved are exquisitely balanced. Yet even these experiments leave gaps. Saturn's hexagon isn't just a fleeting lab curiosity, it's a planetary scale feature enduring through seasons and storms. Some theorists suggest the planet's deep internal heat and rapid rotation act like a cosmic paint mixer, driving jet streams that self-organize into this bizarre shape. Others point to the hexagon's startling alignment with Saturn's rotation axis, hinting that the planet's magnetic field or even deep-seated atmospheric waves might be sculpting the storm from below. Then there's the wild card, standing wave patterns, where oscillations in the atmosphere reinforce each other at just the right frequency to lock in the hexagon's shape against the forces of chaos. What makes the hexagon so mesmerizing isn't just its stability, it's the contrast. At its center lies a churning vortex not unlike Earth's hurricanes, while its edges host smaller storms that scurry like clockwork along its walls, like marbles rolling along a track. Infrared observations reveal the hexagon plunging hundreds of kilometers into Saturn's atmosphere, far deeper than any weather system on Earth, suggesting its roots might tap into energy flows we can't yet measure. The Cassini spacecraft even caught the hexagon changing color with Saturn's seasons, shifting from blue-gold to golden-orange as sunlight played across its cloud tops, a reminder that this isn't just a static sculpture, but a living, breathing weather system. Perhaps the most humbling lesson of the hexagon is how little we understand about planetary atmospheres. Here's a structure that challenges our very definition of storms, one that shouldn't exist according to textbook models. And yet, there it is, spinning silently above Saturn's pole as it has for generations. Every new observation peels back another layer, revealing not just the secrets of a distant planet, but the gaps in our knowledge of the forces shaping worlds everywhere. The hexagon isn't merely a curiosity, it's a masterclass in how nature can sculpt order from chaos, given the right ingredients and enough time. And somewhere in its six-sided symmetry, there might be clues waiting to rewrite how we see atmospheres, both in our solar system and beyond. When the Pan-STARRS telescope in Hawaii first spotted Oumuamua in October 2017, astronomers knew immediately they were looking at something unprecedented. Tumbling through our solar system at nearly 200,000 miles per hour, this interstellar visitor was the first confirmed object from beyond our cosmic neighborhood. But its strangeness only grew with every observation. Unlike the comets or asteroids we're familiar with, Oumuamua defied classification. It had no visible tail of gas or dust, yet it accelerated away from the sun as if propelled by some unseen force. The mystery deepened when researchers reconstructed its shape. Radar measurements suggested an elongated form, possibly 10 times longer than it was wide, like a cosmic cigar hurtling through space. Later analysis pointed to an even stranger possibility. Oumuamua might have been flat, a pancake-shaped object less than a kilometer thick. This pancake scenario raised eyebrows. Natural space rocks rarely form such extreme geometries. They're typically lumpy or spherical from eons of collisions. So how did this thing take on such a peculiar silhouette? Enter Harvard astrophysicist Avi Loeb's controversial hypothesis. Oumuamua wasn't a rock at all, but an artificial light sail, a piece of alien technology designed to harness radiation pressure for propulsion. The math seemed to fit. The visitor's acceleration matched what you'd expect from a thin, reflective sheet pushed by sunlight, like a boat's sail catching the wind. Loeb argued that Oumuamua's tumbling motion and lack of outgassing made more sense if it were a discarded fragment of some advanced civilization spacecraft, perhaps broken off from a larger structure. The scientific backlash was swift. critics pointed out that exotic origins aren't necessary when natural explanations might suffice. Some suggested Oumuamua could be a shard of nitrogen ice, a piece broken off from a Pluto-like exoplanet, so light that solar radiation alone could push it. Others proposed it was a fractal-like dust aggregate, its porous structure explaining both the acceleration and odd shape. The debate raged because by the time telescopes turned toward it, Oumuamua was already too faint to observe further. We'll never get another chance to study it directly. What lingers isn't just the question of what Oumuamua was, it's what its visit represents. Interstellar objects likely pass through our solar system all the time, unnoticed. Oumuamua was the first we caught, a fleeting glimpse into the diversity of material drifting between stars. Whether it was a nitrogen iceberg, an alien artifact, or something else entirely, its very existence forces us to reconsider how much we don't know about the building blocks of the cosmos. The next time an interstellar visitor arrives, and there will be a next time, we'll be watching more closely, armed with the unsettling knowledge that the universe is far stranger than our textbooks ever suggested. Some of the universe's most breathtaking beauty emerges from chaos supernova painting the sky with vibrant remnants, nebulae swirling like cosmic watercolors. Then there's the Red Rectangle Nebula, a structure so precise it looks like it was drafted by celestial architects. Nestled 2,300 light-years away in the constellation Monoceros, this glowing trapezoid of crimson light defies the usual organic swirls of stellar nurseries. Its sharp angles and symmetrical crossbeams seem more like a stained glass window than a natural astronomical formation, leaving scientists to wonder what kind of cosmic forces could forge such geometric perfection. The secret might lie at the nebula's heart, where a pair of aging stars perform a delicate gravitational dance. Known as HD 44179, this binary system consists of a dying star shedding its outer layers and a smaller companion star locked in a tight orbit. As the primary star expels gas and dust in its death throes, the smaller star's gravity sculpts that material into twin cones, their bases meeting to form the nebula's iconic X shape when viewed from Earth. But here's the twist: those cones aren't smooth. They're etched with a series of evenly spaced concentric rings like ripples frozen in time. Some researchers believe these rings are the echoes of periodic outbursts from the central star, pulsing every few centuries as it sheds mass in fits and starts. Others propose they're signs of crystallized carbon dust, microscopic diamonds forged in the stellar winds and reflecting light with uncanny precision. Then there's the color, that deep, blood-red glow unlike anything else in the cosmos. Most nebulas shine with the blues and greens of ionized oxygen or hydrogen, but the red rectangle's hue comes from a rare form of organic molecules called polycyclic aromatic hydrocarbons. These complex carbon chains, illuminated by the central stars, absorb and re-emit light in distinctive crimson bands. It's the same process that gives comet tails their glow, but on a scale so vast it's visible across interstellar space. The eerie part: these molecules are considered building blocks for life. Could this geometric marvel be a cosmic factory for the ingredients of biology? What truly captivates astronomers isn't just the nebula's present form, it's the glimpse it offers into our own future. In roughly 5 billion years, our Sun will undergo a similar transformation, swelling into a red giant and shedding its outer layers. Without a binary companion to shape that material, our solar system's farewell performance will likely be a more chaotic affair. The red rectangle stands as a reminder that even in death, stars can create art, their final acts governed by physics yet yielding structures of haunting symmetry. It's a cosmic paradox, a monument to order carved by violence, a fleeting masterpiece that will dissolve into the void within a few thousand years, leaving only whispers of its once perfect angles drifting among the stars. Hovering silently in the darkness above our planet, The so-called Black Knight satellite has fueled speculation for decades. A shadowy object, some claim, is an ancient alien probe watching Earth from orbit. The legend began in the 1950s when unidentified radio signals allegedly echoed from space, followed by grainy photographs of a peculiar dark shape circling our world. Conspiracy theorists latched onto the idea that this could be extraterrestrial technology, perhaps left behind by a long-gone civilization or even monitoring humanity's progress. The stories grew wilder with time, whispers that it predated human spaceflight, that NASA covered up its existence, that it transmitted signals toward the star system Epsilon Boötis. But like all good myths, the truth is far stranger than fiction. What's actually out there starts with the radio signals. In the late 19th century, Nikola Tesla reported picking up mysterious repeating pulses. Some now argue these were early intercepts of the Black Knight. Later, in 1928, Norwegian engineers detected similar, long-delayed echoes of their own transmissions bouncing back from space. While intriguing, scientists have plausible explanations, from atmospheric reflections to freak ionospheric conditions. As for the photographs, most have been debunked as misidentified space debris or even thermal blankets lost during spacewalks. One famous image from the 1990s, often cited as proof, turned out to show a discarded insulation blanket from an International Space Station mission, a mundane object drifting harmlessly in orbit. Yet the myth persists, and there's a fascinating reason why. The human brain excels at finding patterns even where none exist. A tumbling piece of space junk caught in the right light can look eerily deliberate. Combine that with our cultural obsession with extraterrestrial life, and you have the perfect recipe for a legend that refuses to die. Astronomers point out that an object the size of the alleged Black Knight would have been spotted by now. Our orbital tracking systems monitor everything from spent rocket stages to lost tools. Still, the mystery taps into something deeper, our unease about what might be lurking unseen in the vastness just beyond our atmosphere. Perhaps the most compelling twist isn't whether the Black Knight exists, it's why we so desperately want it to. The idea of an ancient sentinel watching from the stars speaks to our loneliness as a species, our hunger for proof that we're not alone in the cosmos. Every era projects its fears and hopes onto the unknown, and in the space age, our myths have simply taken flight. So the next time you hear about the Black Knight, remember, the real story isn't about alien technology. It's about us staring into the void and wondering if something or someone is staring back, stretching across an incomprehensible 10 billion light-years of space. The Hercules Corona Borealis Great Wall isn't just a structure, it's a cosmic rule breaker. Imagine a tapestry of galaxies so vast it would take light, the fastest thing in the universe, 10 billion years to cross from one end to the other. That's longer than Earth has existed, longer than the sun has burned, longer than the Milky Way's spiral arms have turned. And here's what truly defies logic. According to our best models of the universe, something this colossal shouldn't exist at all. The story begins in 2013, when astronomers mapping gamma ray bursts, the brightest explosions in the cosmos noticed an eerie pattern. These bursts weren't scattered randomly across the sky. Instead, they clustered along an unfathomably large arc stretching from the constellations Hercules to Corona Borealis. Each burst marked the death of a massive star, a beacon signaling the presence of a distant galaxy. Together, they painted the outline of a structure so gigantic it challenged the very foundation of modern cosmology, the cosmological principle. This bedrock idea states that on the largest scales, the universe should look roughly the same no matter where you're standing. Matter ought to be evenly distributed like foam in a well-stirred latte. But the Great Wall, it's more like finding a single continent-sized bubble floating in your coffee. So how did something this immense form? One theory points to the quirks of the early universe. During inflation, the period of rapid expansion just after the Big Bang, tiny quantum fluctuations might have stretched into vast overdensities, seeding regions where galaxies would later cluster in unimaginable numbers. Another possibility is even more mind-bending. What if the Great Wall isn't a single structure at all, but a visual illusion caused by multiple galaxy clusters lining up along our line of sight like celestial beads on a string? Yet detailed 3D maps suggest otherwise. The galaxies in this region share similar redshifts, meaning they're genuinely bound together in space, not just aligned by chance. The implications keep cosmologists up at night. If structures this size are possible, does that mean our universe is far lumpier than we thought? Could there be even larger walls lurking beyond our observational limits, waiting to be discovered? Some researchers argue the Great Wall might force us to reconsider the nature of dark energy, the mysterious force accelerating the universe's expansion. If dark energy's push were slightly weaker in certain regions, it might allow matter to clump on scales we once deemed impossible. Others wonder if we're seeing the fingerprints of exotic physics, primordial magnetic fields, extra dimensions, or even relics from a pre-Big Bang universe. What makes the Hercules Corona Borealis Great Wall so humbling isn't just its scale. It's the reminder that every time we think we've grasped the universe's rules, it throws us a curveball. Here's a structure so vast it dwarfs superclusters, defies models, and whispers that our cosmic maps might still be missing whole continents of the unseen. And as telescopes grow more powerful, who knows what other giants might emerge from the darkness, waiting to rewrite what we thought we knew about the architecture of existence itself. The cosmic microwave background is often called the universe's baby picture, a near-perfect snapshot of the cosmos just 380,000 years after the Big Bang, its subtle temperature variations revealing the seeds of all future structure. But in the constellation Eridanus, there's a patch of sky that doesn't fit the baby picture at all. Stretching nearly 2 billion light-years across, this chilling expanse, dubbed the Eridanus supervoid, is one of the largest and coldest regions ever discovered in the CMB, a cosmic cold spot so profound it defies conventional explanation. Temperatures here dip roughly 70 microkelvin below the surrounding average, as if some unseen hand scooped out a chunk of the early universe and left behind a freezer burn on the fabric of reality. At first glance, the cold spot might seem like a statistical fluke. After all, randomness should produce some outliers, but the odds of a fluctuation this extreme? Less than 1 in 200,000. Cosmologists have proposed 2 leading theories, each more mind-bending than the last. The first suggests the supervoid is exactly what it sounds like, a staggeringly vast bubble of relative emptiness where galaxies and galaxy clusters are sparser than anywhere else we've mapped. In an expanding universe, photons climbing out of such a void would lose energy, shifting to longer, colder wavelengths, an effect known as the integrated Sachs-Wolf effect. But here's the catch, even the largest known voids only stretch a few 100 million light-years. To explain the Eridanus cold spot scale, we'd need a void 10 times larger than anything our models predict should exist. That's where the second theory comes in, one that ventures into speculative physics. Some researchers propose the cold spot might be a cosmic bruise, evidence of a collision with another universe during the chaotic early moments of inflation. In this scenario, our universe's rapid expansion could have created a bubble of spacetime adjacent to others in a vast multiverse. If 2 bubbles grazed each other, the energy released might have left behind a defect in spacetime structure, a region where density and temperature dropped precipitously. The idea isn't as far-fetched as it sounds. Certain string theory models predict exactly this kind of imprint, a fingerprint of worlds beyond our own. Yet even these radical explanations struggle to account for all the data. Detailed galaxy surveys show no void large enough to fully explain the cold spot's temperature dip, while simulations of bubble collisions produce scars that don't quite match the Eridanus anomalies profile. The truth might lie somewhere in between, perhaps a combination of smaller voids aligned along our line of sight, amplified by something stranger still. Or maybe we're seeing the limits of our own models, a hint that dark energy, inflation, or even gravity itself behave differently on scales we've barely begun to probe. What makes the Eridanus supervoid so compelling isn't just its mystery, it's the questions it forces us to confront. Are we staring at a flaw in our understanding of cosmic structure, or a window into realms beyond our universe? Every new observation tightens the knot. The Planck satellite's data confirmed the cold spot's reality, while upcoming telescopes like LSST could finally map its underlying structure in unprecedented detail. Until then, it remains a cosmic Rorschach test, a blank spot on the map that invites us to dream bigger, to consider that the universe's grandest mysteries might not just lie in the stars, but in the silent, icy gaps between them. If you've ever found yourself under a truly dark sky just before dawn or after sunset, you might have noticed something strange, a faint, ghostly glow stretching upward from the horizon, like a celestial pyramid of muted light. This isn't some trick of the eyes or distant city lights, it's the zodiacal light, one of the solar system's most haunting and misunderstood phenomena. Caused by sunlight scattering off trillions of dust particles drifting between the planets, this ethereal glow has puzzled astronomers for centuries. And here's the twist: the more we study it, the less it makes sense. The conventional explanation seems straightforward enough. Over millennia, comets barreling through the inner solar system shed dust as their ices vaporize, leaving behind trails of debris. Asteroids, too, chip and collide, adding to the cosmic dust budget. Sunlight pushes these particles into a vast, lens-shaped cloud centered on the Sun. And when Earth's orbit carries us through this dusty disk, we see the scattered light as a soft cone rising along the ecliptic, the path the zodiac constellations follow. Simple, right, except the numbers don't add up. Recent measurements from spacecraft like NASA Juno probe reveal a dust distribution that defies expectations. There's too much material too close to the Sun, and the particles are bigger and more evenly spread than comet models predict. Some researchers argue this points to an overlooked source, perhaps violent collisions in the asteroid belt spewing coarser debris, or even interstellar dust grains snagged by the Sun's gravity. Others suggest a more provocative idea. What if the zodiacal dust isn't ancient at all, but constantly replenished by an unseen population of dark comets, icy bodies that stealthily shed material without the usual glowing tails? Then there's the mystery of asymmetry. The zodiacal light should, in theory, be uniform, a symmetrical haze aligned with the solar system's plane. But detailed observations show odd bright spots and warps, as if the dust cloud has been stirred by some invisible hand. Could planetary gravity be sculpting these patterns, with Jupiter's mighty pull creating density waves? Or are we seeing the aftermath of a recent, catastrophic breakup, a rogue asteroid or comet that shattered and left its guts smeared across the inner system? The implications reach far beyond a pretty glow. Zodiacal dust is more than just cosmic decoration. It's a hazard for spacecraft, a lens for studying the solar system's history, and even a potential delivery system for organic molecules to young planets. If we've misjudged its origins, we might be missing a key piece of how our own cosmic neighborhood evolved. Every unanswered question, from the dust's peculiar composition to its uneven spread, hints at processes we've yet to uncover. A hidden chapter in the solar system's story, written in particles too small to see but too vast to ignore. So the next time you catch that faint, otherworldly light rising from the horizon, remember, you're not just looking at comet dust. You're staring at a cosmic crime scene, a puzzle scattered across the sky, waiting for someone to piece together the clues. At first glance, Hoag's object looks like someone dropped a cosmic bullseye into the depths of space. A perfect ring of blue stars encircling a golden core, floating in isolation against the black velvet of the universe. Discovered in 1950 by astronomer Art Hoag, This bizarre galaxy defies every expectation of how galaxies form and evolve. Most ring galaxies, like the famous cartwheel, owe their shape to violent collisions, one galaxy punching through another, sending shockwaves that trigger star formation in a radiant circle. But Hoag's object, there's no sign of a culprit, no neighboring galaxy that could have caused this breathtaking structure. It's as if this celestial jewel formed in pristine solitude, a puzzle wrapped in starlight. The mystery deepens when you peer closer. The inner core of Hoag's object is a dense sphere of ancient yellow stars, typical of elliptical galaxies. The outer ring, though, is a stellar nursery, young, hot stars blazing in a near-perfect loop 12 billion miles wide. Stranger still, there's an eerie gap between the core and the ring, a dark band where almost no stars reside. How could such a clean separation occur naturally? Some theories suggest a long-ago encounter with another galaxy, but the lack of distortion in the ring's shape makes this unlikely. Others propose an instability in the galaxy's rotation, where gas pooled at certain distances before collapsing into stars. Yet simulations struggle to recreate Hoag's object's symmetry without invoking some cataclysmic event. Then there's the enigma of its loneliness. Most galaxies live in clusters, gravitationally bound to neighbors in a cosmic dance. Hoag's object floats alone, its nearest galactic companion over 600,000 light-years away, too distant to have influenced its peculiar form. This isolation raises tantalizing questions. Could it be a rare example of a galaxy forming from a primordial gas cloud that somehow avoided the usual mergers and collisions? Or is it the aftermath of a freak event, like a central black hole ejecting stars in a precise outward wave? The plot thickens when astronomers spotted something even weirder, another, fainter ring galaxy lurking in the background of Hoag's object's own image, visible through the gap in its ring. This chance alignment suggests ring galaxies might be more common than we thought, hiding in plain sight. It's a cosmic Russian doll, one mystery nested inside another. For now, Hoag's object remains a celestial oddity, a silent challenge to our understanding of galactic evolution. Every observation peels back another layer, revealing not just the secrets of one strange galaxy, but the gaps in our knowledge of how all galaxies sculpt themselves across the eons. Deep in the cosmos, something impossible is happening. Entire galaxy clusters are racing toward a point beyond the edge of everything we can see, as if tugged by the gravitational hand of something outside our universe. Astronomers call this the dark flow, and it's exactly as unsettling as it sounds. Picture a river of galaxies, thousands of them, all streaming in the same direction at speeds topping 2 million miles per hour, toward a region of space with no known mass, no visible supercluster, nothing that could explain such a coordinated motion. This isn't just peculiar, it defies one of cosmology's core principles, that the universe on the largest scales should be uniform. There shouldn't be a direction to things. Yet the dark flow suggests something massive, something unseen, is pulling on us from beyond the observable horizon. The discovery came from studying the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light reveal how matter moves across the universe. But when scientists mapped the motion of galaxy clusters using these ripples, they found a pattern that shouldn't exist. The clusters weren't just drifting apart with the expansion of space. They were being dragged en masse toward a single patch of sky near the constellations Centaurus and Vela. The kicker, the source of this pull lies farther than light has had time to travel since the universe began. It's not just hidden, it's literally outside our field of view, in a region of space-time we can never observe. Theories scramble to explain it. One radical idea posits that the dark flow is evidence of other universes, cosmic bubbles, floating in a vaster multiverse, each with its own physics and structure. If one of these bubbles brushed against ours during inflation, its gravitational influence might still linger, tugging galaxies like a distant magnet. Others suggest it could be a remnant of the pre-Big Bang universe, a scar from an earlier epoch that imprinted itself on the fabric of reality. Skeptics argue it's a measurement error or an artifact of incomplete data, but the signal persists across multiple studies, growing harder to dismiss with each new survey. What makes the dark flow so unnerving isn't just its existence, it's the possibility that we're seeing the limits of our cosmic map. The observable universe might just be a tiny island in an ocean of unseen realms, their gravity reaching across the void to sway everything we know. If true, it means the grand story of the cosmos doesn't end at the edges of our telescopes. There's something out there, something we can't see, can't touch, but whose presence is written in the silent rush of galaxies fleeing toward the dark. Beneath the serene glow of the Milky Way's spiral arms, a sleeping giant lurks, our galaxy's supermassive black hole, Sagittarius A. While it may seem quiet now, some scientists believe it has a violent, cyclical secret, apocalyptic bursts of energy called galactic superwaves. These aren't just flares or radiation spikes, they're tsunamis of gamma rays and cosmic rays, erupting from the galactic core in waves so powerful they could sterilize entire swaths of the Milky Way. And chillingly, there's evidence Earth might have weathered these storms before, with catastrophic consequences for life itself. The theory traces back to physicist Paul Laviolette, who proposed that Sagittarius doesn't just occasionally snack on passing stars. It periodically erupts in cataclysmic outbursts, triggered by surges of infalling matter or instabilities in its accretion disk. When this happens, the black hole doesn't just burp, it screams. Imagine a shockwave of high-energy radiation expanding outward at near light speed, carving through interstellar gas like a cosmic bulldozer, accelerating particles to unimaginable energies along the way. By the time such a wave reaches the outer galaxy, it's no longer just a flash of light. It's a rolling front of destruction, capable of frying unprotected planets and stripping atmospheres. What gives this idea teeth are the eerie parallels in Earth's own geological record. Mass extinctions like the Ordovician-Silurian event 440 million years ago align suspiciously with evidence of sudden, intense radiation bombardment. Fossil records show abrupt drops in biodiversity, while isotopes like iron-60 in ancient ocean sediments hint at nearby supernova, or something equally violent. But supernovae are random, scattered events. Galactic superwaves offer a more sinister possibility, a ticking clock with extinctions timed to the rhythm of our galaxy's hidden heart. The mechanics are even more unsettling. As the wave plows through interstellar space, it doesn't just deliver a single pulse of radiation. It compresses dust and gas ahead of it, creating a shock front that can trigger secondary supernova. Picture a domino effect where the initial wave sets off stellar explosions in its path, amplifying the destruction. Some models suggest these waves could even destabilize the Oort cloud, sending comets hurtling toward the inner solar system in a deadly hailstorm. It's a triple threat: radiation, supernova, and icy projectiles, all orchestrated by a single galactic tantrum. Yet for all its terrifying potential, the galactic superwave theory remains controversial. Critics point out that Sagittarius A's current activity is too mild to suggest such outbursts, while others argue extinction timelines don't neatly match proposed wave cycles. Still, the circumstantial evidence is hard to ignore. Ice cores from Antarctica reveal spikes in cosmic ray exposure dating back 12,000 years around the Younger Dryas period, a time of abrupt climate upheaval and megafauna extinctions. Could a near-miss superwave have brushed past Earth, leaving scars in our atmosphere and myths of global fire in ancient cultures? The deeper we look, the more the galaxy seems less like a peaceful haven and more like a sleeping dragon, stirring occasionally with world-shaking force. Whether these superwaves are real or not, the possibility forces us to confront an uncomfortable truth. We're not just passengers on a quiet planet orbiting a stable star. We're living in the blast zone of a cosmic powerhouse, one with a temper we're only beginning to understand. and if the pattern holds, the next wave might already be on its way, a silent ripple in the dark carrying echoes of the apocalypse. Somewhere in the heart of the Perseus galaxy cluster, a cosmic oddity floats like a ghostly jellyfish NGC 1275's infamous blob, a gargantuan cloud of gas that refuses to play by the rules. Stretching over 20,000 light-years, this glowing mass of hydrogen should have been ripped apart by now, shredded by the violent forces of its environment. Galaxy clusters are cosmic war zones filled with superheated gas and gravitational turbulence strong enough to tear apart stars. Yet here it is, drifting serenely for billions of years, birthing new stars against all odds. The mystery isn't just what the blob is, it's how it survives in a place where nothing so delicate should last a day. The first clue lies in the blob's bizarre structure. Unlike typical gas clouds which disperse under pressure, this one's held together by an invisible scaffold of magnetic fields. Imagine a spiderweb threaded through smoke, keeping it intact against hurricane winds. These fields, likely woven by the galaxy's supermassive black hole, act like cosmic rebar, reinforcing the gas against the cluster's onslaught. But there's a twist. The blob isn't just clinging to life. It's thriving, glowing with the blue light of young stars, as if it's drawing energy from the chaos around it. That's the second puzzle. Star formation usually stops in hostile environments, where turbulence prevents gas from cooling and collapsing. Yet the blob defies this, turning destruction into creation. One theory suggests the secret is in the dance of heat and motion. The Perseus cluster is bathed in scorching plasma, but simulations show the blob might be riding shockwaves like a surfer on a tidal surge. As galaxy collisions send ripples through the cluster, these waves could compress the gas just enough to trigger star formation, even as the larger environment tries to tear it apart. It's a cosmic balancing act. Too much turbulence and the cloud shreds just enough and it thrives. Then there's the black hole connection. NGC 1275's core is a monster, spewing jets of particles at nearly light speed. These jets could be injecting energy into the blob, not destroying it but stabilizing it. Picture a chef whisking a sauce to keep it from curdling. The black hole's outbursts might be stirring the gas just enough to prevent collapse or dispersion. It's a delicate feedback loop where destruction and creation exist in an uneasy truce. What makes the blob so mesmerizing isn't just its defiance of physics, it's the way it mirrors life's own stubbornness. Against all odds, in the harshest corners of the universe, pockets of order emerge from chaos, crafting beauty where none should exist. Whether it's magnetic armor, shockwave surfing, or black hole alchemy, the blob stands as a testament to nature's ingenuity. And as telescopes peer deeper into its shimmering depths, one thing's certain: the universe writes its own rules, and we're just beginning to decipher them. Every second, trillions of cosmic rays, subatomic particles flung across space at nearly light speed, rain down on Earth's atmosphere. Most are harmless, their origins traced to nearby supernova or the sun's eruptions. But occasionally, detectors catch something staggering: a single proton or atomic nucleus carrying as much energy as a major league fastball, packed into a particle smaller than an atom. These ultra-high-energy cosmic rays shouldn't exist. According to everything we know about physics, they should have been obliterated long before reaching us, shredded by photons in the cosmic microwave background as they traversed the void. Yet here they are, arriving in defiance of the universe's most ironclad rules. This is the Greisen-Zatzeping Kuzmin paradox, or GZK paradox, a cosmic whodunit that's been baffling physicists for over half a century. The crux of the problem lies in the simplest law of particle physics. Energy can't just vanish. When an ultra-high-energy cosmic ray, some packing over 100 exa-electronvolts, millions of times more powerful than anything produced in human-made colliders, travels through space, it should collide with the ever-present photons of the CMB, the afterglow of the Big Bang. These collisions ought to sap the particle's energy through a process called photopion production, where interactions spawn new particles that bleed off momentum. Calculations from the 1960s by Grison, Zatsepin, and Kuzmin showed that over distances beyond 50 megaparsecs, roughly 160 million light-years, these rays should be reduced to cosmic roadkill. Yet observatories like the Pierre-Auger array keep catching them, some with paths suggesting origins far beyond that theoretical limit. It's like finding an arrow shot from a bow halfway across the world, still traveling at full speed when it lands in your backyard. So where's the disconnect? One possibility is that our models of particle interactions at these extreme energies are incomplete. Perhaps unknown quantum effects or exotic physics kick in at energies so high they've never been replicated in labs, allowing particles to slip past the CMB's defenses. Some theorists propose Lorentz invariance violation, a crack in Einstein's relativity that would let particles cheat the universe's speed and energy limits. Others suggest these rays aren't protons at all, but heavier nuclei like iron, which might interact differently with the CMB. But even these explanations dance around a deeper question: what cosmic engine could possibly produce such particles in the first place? The suspects are as extreme as the mystery demands. Active galactic nuclei, where supermassive black holes spew jets of plasma at relativistic speeds, are prime candidates, except their known emissions don't quite match the energy spectrum we observe. Colliding galaxy clusters with their titanic shockwaves could act as particle accelerators on a scale dwarfing the Large Hadron Collider, but simulations struggle to account for the highest energy events. Then there's the wild card: topological defects, hypothetical remnants of the early universe's phase transitions, decaying and releasing bursts of energy that make supernova look like firecrackers. The GZK paradox isn't just a puzzle, it's a pressure point where our understanding of particle physics, cosmology, and astrophysics collide. Every detected ultra-high-energy cosmic ray is a flare in the dark, hinting at forces or phenomena we've yet to imagine. Whether it's hidden physics, cosmic accelerators beyond our current catalog, or something entirely unforeseen, the answer won't just solve a 50-year-old riddle. It could rewrite the rules of how energy, matter, and the fabric of space-time itself behave at the universe's most violent extremes. Until then, these particles keep arriving, silent and inexplicable, each one a bullet fired from the edge of the known cosmos. We think we know what the universe is made of until we start counting, and when we do, the numbers don't add up. Dark matter and dark energy might dominate the cosmic budget, but even the ordinary matter we can see, the stuff of stars, planets, and human bodies, has pulled a vanishing act. About half of it is simply missing. These are the universe's lost baryons, the protons and neutrons that should be scattered throughout space, yet somehow evade detection in our most thorough surveys. To put it in perspective, if every atom in all the stars, galaxies, and gas clouds we've observed were gathered together, they'd account for less than half the baryons predicted by Big Bang nucleosynthesis. So where's the rest of the universe's ordinary matter hiding? The answer might lie in the cosmic web, the vast, invisible scaffolding that stretches between galaxies. This isn't just empty space. Simulations predict that nearly all the missing baryons are woven into faint, superheated filaments of gas, a diffuse network so thin and spread out it's nearly transparent. Picture a sponge soaked in water where the liquid clings to every strand. Now imagine that sponge light years across, with gas so scorching somewhere between 10,000 and 10 million degrees, it glows only in X-rays, invisible to optical telescopes. These faint tendrils, known as the warm-hot intergalactic medium, or WIM, are thought to contain the bulk of the universe's missing normal matter, tracing the same gravitational web that funnels galaxies into clusters and voids. For decades, detecting the WIM seemed impossible. Its particles are too sparse to cast shadows, too hot to form molecules, and too dim against the cosmic X-ray background. But astronomers have begun pulling back the curtain with clever tricks. One method involves quasars, the blazing cores of distant galaxies whose light pierces through the cosmic web like a flashlight beam. As this light travels, certain wavelengths get absorbed by ionized oxygen and other elements in the WIM tendrils, leaving faint fingerprints in the quasar's spectrum. Another approach hunts for the WIM's own faint X-ray glow, using sensitive detectors to pick up wisps of emission between galaxy clusters. The European Space Agency's XMM-Newton telescope and NASA Chandra Observatory have both spotted tantalizing hints, with X-ray absorption lines matching predictions for these elusive filaments. Yet the puzzle isn't fully solved. Even accounting for the WIM's scattered gas, some baryons remain unaccounted for, leading to wilder theories. Could they be hiding in the form of primordial black holes, smaller than atoms but numerous enough to tip the cosmic scales? Or might they lurk in compact, cold clouds of molecular hydrogen, too faint for current telescopes to spot? The hunt has even turned to our own backyard. Some propose that a fraction of the missing matter could be drifting undetected through the solar system, invisible except through subtle gravitational tugs. What makes this cosmic accounting so compelling isn't just the mystery of the missing matter. It's the realization that the universe's scaffolding might be far richer than we ever imagined. These ghostly filaments aren't just hiding baryons. They're the highways along which galaxies form, the channels through which energy flows, and perhaps even the reservoirs feeding future star formation. As telescopes grow more sensitive, the invisible web might finally step into the light, revealing not just where the missing matter went, but how the universe stitches itself together on the grandest scales. Until then, every new observation tightens the net, bringing us closer to closing the case on one of cosmology's greatest disappearing acts. In the endless dance of cosmic giants, black holes are supposed to be the anchor's gravitational monsters sitting firmly at the hearts of galaxies, dictating the motion of stars with their immense pull. But in 2023, the Hubble Space Telescope spotted something that shattered this assumption. A supermassive black hole weighing as much as 20 million suns, barreling through intergalactic space like a rogue bullet. And the strangest part, it wasn't alone. Behind it stretched a never-before-seen trail of newborn stars, a luminous scar stretching 200,000 light-years long, twice the diameter of our entire Milky Way. At first glance, the scene defied logic. Black holes don't just pack up and leave. Their gravity is so overwhelming that escaping a galaxy's core should be impossible. Yet here was undeniable proof, a monster in motion, racing away at 4 million miles per hour, fast enough to travel from Earth to the Moon in under 15 minutes. The leading theory is as dramatic as the discovery itself. This black hole was likely ejected during a violent galactic merger. Picture two galaxies colliding, their central black holes spiraling toward each other in a gravitational tango. As they merged, the energy released could have been so immense that it acted like a cosmic slingshot, flinging the newly formed black hole into the void. Simulations suggest such events are rare but possible, a reminder that the universe has a flair for the catastrophic. What makes this runaway truly bizarre, though, isn't just its speed, it's the star-studded wake it left behind. Normally, black holes are destroyers, shredding stars and swallowing gas. But Hubble's images revealed the opposite, a narrow corridor of young, blue stars glowing like cosmic streetlights along the black hole's path. The explanation, as the black hole plowed through intergalactic gas, the shockwaves likely compressed and heated the material in its wake, igniting star formation in its turbulent wake. Think of it like a ship's bow wave, but instead of water, it's churning space itself into stellar nurseries. The implications are staggering. If black holes can be ejected from their galaxies, how many others are drifting unseen in the darkness? Could these nomads seed star formation in the most desolate corners of the universe? And what happens to the galaxies they leave behind? A supermassive black hole isn't just a silent anchor. It regulates star birth, shapes galactic structure, and even influences the distribution of dark matter. A galaxy losing its central black hole might age differently, its evolution thrown into chaos. Yet for all the questions, one thing is certain. This discovery proves the cosmos still holds surprises that append our textbooks. The idea of a black hole as a cosmic wanderer trailing starlight in its wake feels more like science fiction than observed reality. But there it is, a runaway giant carving a path through the void, reminding us that even the universe's most predictable titans can sometimes break free. High above the galactic plane, a lone star glows with the quiet defiance of time itself, HD 140283, better known as the Methuselah star. Estimated to be a staggering 14.5 billion years old, this ancient relic of the cosmos presents a paradox that rattles the foundations of modern cosmology. How can a star exist that's older than the universe itself? Current estimates place the age of the universe at 13.8 billion years, leaving the Methuselah star appearing nearly a billion years its senior. It's like finding a birth certificate that predates the invention of calendars. The star's age was first calculated using its composition, a metal-poor subgiant brimming with hydrogen but nearly devoid of heavier elements. Stars like this are cosmic fossils, formed when the universe was still in its infancy, before supernova had seeded space with the building blocks of planets and life. By measuring its brightness, temperature, and distance thanks to precise Hubble Space Telescope observations, astronomers pieced together its life story. But when the numbers came back, they pointed to an impossible timeline. Revised Hubble data softened the blow slightly, adjusting the star's age downward to around 14.5 billion years, but even this leaves an uncomfortable gap. Cosmologists have scrambled to reconcile the discrepancy. Some argue the star's age might overlap with the universe's own if we account for margin of error, a blurry boundary where 13.8 and 14.5 billion could almost shake hands. Others suggest the Methuselah star might have formed from a pocket of primordial gas untouched by the turbulence of the early universe, allowing it to ignite sooner than typical stellar nurseries. But these explanations feel like patches on a leaking dam. The real tension lies in the assumptions baked into our cosmic clocks. The universe's age is calculated from the cosmic microwave background, the afterglow of the Big Bang, combined with measurements of its expansion rate. The Methuselah star's age, meanwhile, relies on stellar evolution models' equations that describe how stars burn fuel, collapse, and fade. If there's a flaw in either framework, the consequences ripple far beyond one stubborn star. Could dark energy be skewing our perception of cosmic time? Or might the early universe have cooled faster than we thought, letting stars form in a flash of premature brilliance? What makes this celestial elder so captivating isn't just the math, it's the philosophical weight of its existence. The Methuselah star forces us to confront the limits of our knowledge, a reminder that even the most precise measurements can crumble when faced with the universe's stubborn complexity. Whether it's a statistical outlier, a clue to new physics, or simply a cosmic joke written in starlight, one thing's certain: this ancient sentinel isn't just breaking the rules of time, it's rewriting them. At the frozen edges of our solar system, where sunlight is reduced to a dim twilight, something massive seems to be warping the paths of distant icy worlds. Astronomers call it Planet 9, a hypothetical giant, possibly 10 times Earth's mass, lurking hundreds of times farther from the Sun than we are. The evidence: a peculiar clustering of Kuiper belt objects, small icy bodies orbiting beyond Neptune, whose elongated paths all point in the same direction as if nudged by an unseen hand. These orbits aren't just randomly scattered. They're aligned with a precision that defies the odds, like compass needles all pointing toward a hidden magnet. The case for Planet 9 began in earnest in 2016 when astronomers Konstantin Batygin and Mike Brown noticed this bizarre orbital pattern. 6 extreme trans-Neptunian objects, icy worlds like Sedna and 2012 VP113, shared nearly identical angles of perihelion, the point where they swing closest to the Sun. Simulations showed the chance of this alignment happening naturally was less than 0.0007%. Add to this the discovery of other Kuiper belt objects with orbits tilted steeply out of the solar system's plane, and the picture grew even stranger. The simplest explanation, a distant, undiscovered planet, its gravity shepherding these objects into their odd configurations over billions of years. But not everyone is convinced. Some researchers argue the data could be skewed by observational bias after all. These objects are incredibly faint, and we've only spotted a handful. Others propose a radical alternative. What if gravity itself behaves differently in the outer solar system? Modified Newtonian dynamics, or MUND, suggests that on very large scales, gravity doesn't follow Einstein's rules exactly. In this view, the peculiar orbits might not require a hidden planet at all, but rather reflect a fundamental quirk in how gravity operates where the Sun's pull grows weak. The debate highlights a fascinating tension in science. Planet 9 advocates point to its elegance, a single explanation for multiple anomalies, much like Neptune's prediction from Uranus's orbital wobbles in the 19th century. Yet skeptics caution that invoking unseen worlds risks repeating history's mistakes, like the once hypothesized Vulcan to explain Mercury's precession, later overturned by relativity. The truth might lie somewhere in between. Could there be a smaller, closer object like a primordial black hole or a rogue ice giant ejected long ago? Or might the answer require us to rethink our cosmic neighborhood entirely? For now, the hunt continues. Telescopes scour the outer darkness, searching for the faint infrared glow a distant planet might emit. Meanwhile, simulations explore whether passing stars or galactic tides could mimic Planet 9's effects. What's certain is this: whether it's a hidden world or a sign of new physics, the outer solar system holds mysteries that could redefine our place in the cosmos. The real discovery won't just be an object, it'll be a lesson in how much we have yet to learn. High above Venus's scorching surface, where the air is thick enough to crush submarines and the heat could melt lead, something impossible is happening. A colossal vortex spanning thousands of miles spins endlessly at the planet's south pole, a storm with not one but two distinct eyes swirling in a hypnotic dance of gas and fury. This isn't just another planetary storm. It's a meteorological freak, a structure so bizarre that nothing like it exists anywhere else in the solar system. And the strangest part, we're still not entirely sure how it survives in Venus's hellish atmosphere. The vortex was first spotted by the European Space Agency's Venus Express orbiter in 2006, but its roots might stretch back much further. Earth-based observations and NASA, a pioneer Venus mission in the 1970s, hinted at polar disturbances, but it took modern instruments to reveal the full spectacle. Unlike Jupiter's Great Red Spot, a stable hurricane raging for centuries, or Saturn's polar hexagon, a geometric oddity carved by jet streams, the Venus vortex is shockingly dynamic. Its shape morphs constantly, sometimes a figure 8, other times an elongated S, even splitting into separate spirals before merging again, and it's fast. Winds whip around its edges at over 200 miles per hour, yet the core remains eerily calm, a quiet eye in a maelstrom of superheated gas. What keeps this atmospheric monster alive? The leading theory points to Venus's superrotation, a phenomenon where the planet's atmosphere spins 60 times faster than its surface. This creates colossal wind shear, twisting and stretching air masses into vortices. At the poles, these forces could funnel gases downward, creating a permanent low-pressure zone that acts like a drain, pulling the vortex into existence. But the double eye structure defies simple fluid dynamics. On Earth, hurricanes sometimes develop concentric eye walls, but they're unstable and short-lived. Venus's twin cores persist for weeks, even months, suggesting some unseen mechanism is at work. Could atmospheric waves bouncing between the planet's day and night sides be stabilizing the storm? Or is the vortex feeding off heat from Venus's volcanic hotspots below, like a steam engine powered by the planet's fiery belly? Then there's the chemistry. Venus's atmosphere is a toxic soup of carbon dioxide laced with sulfuric acid clouds. As gases churn in the vortex, they might be triggering reactions we've never observed, creating compounds that alter the storm's structure. Infrared data reveals temperature differences between the vortex's cores, hinting at complex energy exchanges beneath the visible chaos. It's a reminder that even in a place as hostile as Venus, nature finds ways to build patterned structures that balance destruction and order on a scale we're only beginning to comprehend. The deeper mystery is why Venus alone hosts such a storm. Mars has polar caps but no vortices. Earth's polar cyclones are fleeting compared to Venus's permanent spectacle. Even gas giants with their endless storms don't produce anything with this dual-core structure. Some scientists speculate the vortex might be a key to Venus's climatic past, a relic from when the planet had oceans, or a sign of deeper atmospheric layers interacting in ways we can't yet model. Every new observation peels back another layer, revealing not just the secrets of a distant storm, but the gaps in our understanding of how atmospheres evolve across the cosmos. For now, the Venus vortex remains a mesmerizing enigma, a whirlwind in a furnace defying expectations, daring us to unravel its secrets. As future probes like NASA, Da Vinci and ESA's Envision mission prepare to study Venus up close, one thing's certain: this isn't just a storm. It's a masterpiece of alien meteorology, a reminder that even our nearest planetary neighbor holds wonders stranger than fiction. And somewhere in its swirling depths, there might be answers waiting to rewrite what we know about the winds of other worlds. For years, the Martian landscape has whispered tantalizing hints of a mystery that could rewrite our understanding of the red planet. Erratic bursts of methane gas detected by NASA Curiosity rover. These fleeting spikes, some as high as 21 parts per billion, vanish almost as quickly as they appear, leaving scientists debating the most profound question of all. Is this the faint signature of life, or just another geological sleight of hand? Curiosity's onboard tunable laser spectrometer first caught the methane in 2013, and the pattern defies easy explanation. Unlike Earth, where methane is continuously replenished by biological activity like bacterial digestion or geological processes like volcanic vents, Mars' methane behaves like a cosmic will-o'-the-wisp. It surges unpredictably, sometimes lingering for weeks, other times disappearing overnight. The rover even recorded a staggering tenfold spike over just 2 months in 2019, a fluctuation so abrupt it suggests a localized, active source. But here's where the plot thickens. While Curiosity sniffed methane at ground level, the European Space Agency's Trace gas orbiter, equipped with far more sensitive instruments, found nothing in the broader atmosphere. Not a trace. This discrepancy isn't just frustrating, it's forcing a radical rethink of how methane behaves on Mars. One possibility: the gas is being destroyed near the surface faster than models predict, perhaps by ultraviolet radiation or chemical reactions with the iron-rich soil. Alternatively, the methane might be seeping from underground reservoirs in such small, isolated pockets that only a rover driving directly over them would notice. The debate over origins is even fiercer. On Earth, most methane comes from living organisms or the breakdown of organic matter. If microbes exist beneath Mars' permafrost, perhaps in briny aquifers shielded from radiation, they could be producing the gas as a byproduct. Yet geology offers equally compelling alternatives. Serpentinization, a process where water reacts with certain minerals like olivine, can generate methane abiotically. Or the gas might be ancient, trapped in ice cages called clathrates for eons before occasional collapses release it in sporadic bursts. What makes this detective story so gripping is the stakes. If the methane is biological, it would be the strongest hint yet that we're not alone in the universe. But even a geological origin would reshape our view of Mars as a dynamic, chemically active world, with hidden reservoirs of water or energy that could one day sustain human explorers. Every new data point, whether from future rovers, orbiters, or even sample return missions, brings us closer to solving a puzzle that's as much about the resilience of life as it is about the secrets of a rusty alien desert. Until then, those fleeting methane whispers remain one of the most tantalizing maybes in planetary science. On the morning of June 30th, 1908, a fireball brighter than the sun tore across the skies of Siberia, flattening 80 million trees across 800 square miles of remote taiga. The Tunguska event remains the most powerful impact in recorded history, a blast roughly 1,000 times more forceful than the Hiroshima bomb, yet left no crater, no fragments, and no obvious culprit. For over a century, this paradox has fueled debates between mainstream science and wilder speculation. Was it a rogue space rock or something far stranger lurking in the cosmic shadows? The conventional explanation points to an airburst, a comet or asteroid exploding in the atmosphere before reaching the ground. Simulations suggest a stony meteor around 200 feet wide, traveling 34,000 miles per hour, could have disintegrated 5 miles up, unleashing shockwaves and thermal radiation without leaving impact scars. Tree patterns support this, trunks fanned outward like matchsticks from a central point, while bizarrely, trees near ground zero remained standing but were stripped bare, as if seared by an invisible heat wave. Yet no trace of the object has ever been found, despite decades of scouring for nickel-iron fragments or comet dust. Even more puzzling, witnesses hundreds of miles away reported eerie atmospheric effects for weeks, glowing nights, silver clouds, even sunsets so bright they cast shadows at midnight. This absence of physical evidence has opened the door to more exotic theories. In the 1970s, physicists proposed a radical alternative. What if a primordial black hole, a hypothetical relic from the Big Bang, smaller than an atom but as massive as a mountain, passed through Earth? Such an object could streak through the planet like a bullet through tissue, exiting near the North Atlantic while compressing air so violently it mimicked a nuclear blast. The math checks out. The shockwave would match Tunguska's profile, and the lack of debris would make sense. But here's the hitch: a black hole transit. It should leave telltale seismic signatures along its path, and no such trail has been found. Another fringe idea involves antimatter annihilation, a chunk of extraterrestrial antimatter colliding with our atmosphere, converting entirely to energy in a flash of gamma rays. While elegant in theory, this raises thorny questions. How would such a fragile substance survive interstellar space, and why hasn't any similar event been recorded since? Even wilder notions hover at the edges. Alien spacecraft malfunctions, Tesla's death ray experiments gone awry, or a dimensional rift briefly puncturing our reality. What makes Tunguska so endlessly fascinating isn't just the unanswered questions, it's the chilling reminder of our planet's vulnerability. If the explosion had occurred 4 hours later, it would have obliterated St. Petersburg. Modern tracking shows similar-sized objects pass uncomfortably close every few centuries, with the Chelyabinsk meteor of 2013 serving as a recent warning shot. Yet Tunguska stubbornly resists categorization, blurring the line between known physics and tantalizing what-ifs. Whether it was a comet's ghostly fingerprint or a crack in the cosmos we still don't understand, one thing's certain: the Siberian wilderness keeps its secrets well. And the next time the sky splits open with such fury, we might not be so lucky. The cosmos rarely gives us a front-row seat to its grandest spectacles until astronomers pointed to the constellation Cygnus and made a staggering prediction. In the binary star system KIC 9832227, 2 stars were spiraling toward a cataclysmic merger, set to explode in a fiery embrace by 2022. The forecast wasn't just bold, it was unprecedented. For the first time, scientists claimed they could pinpoint the exact year a stellar collision would light up Earth's skies, possibly shining as bright as the North Star. The implications were electrifying. A celestial fireworks display visible to the naked eye, a once-in-a-lifetime chance to witness a cosmic rebirth in real time. What made this prediction so audacious was the meticulous detective work behind it. The binary system had been under scrutiny since 2013, when researchers noticed its light curves. The rhythmic dips in brightness as stars orbit each other were changing. The stars, locked in a tight gravitational dance, were circling faster and faster, their orbital period shrinking by a few seconds each year. This accelerating spiral matched computer models of what's called a contact binary, where two stars share a common envelope of gas, dragging each other closer until they merge in a violent outburst known as a red nova. The template for this scenario, V1309 Scorpii, a star that erupted in 2008 after exhibiting eerily similar behavior. If history repeated itself, KIC 9832227 would erupt in a blaze of crimson light, temporarily outshining half the stars in the Milky Way. Yet as the predicted window approached, doubts crept in. Revised calculations suggested the merger might be delayed by years, even decades. Critics pointed to subtle differences between this system and V1309 Scorpii, arguing the star's masses or chemical compositions might alter the outcome. The tension was palpable. Here was a chance to test our understanding of stellar evolution with a real-time experiment, but nature doesn't always follow human timelines. By 2022, no explosion had come. The stars continued their slow-motion tango, indifferent to our anticipation. What makes this story so compelling isn't the failed prediction, it's the glimpse into how science grapples with uncertainty. Astronomers didn't pack up their telescopes, they refined their models, scrutinized new data, and debated alternative explanations. Perhaps the stars won't merge at all but settle into a stable configuration. Or maybe the collision is still coming, a delayed cosmic encore waiting for its cue. The real lesson lies in the humility of the process, a reminder that the universe operates on its own schedule, and our job is to watch, learn, and adapt. Whether the merger happens next year or next century, one thing's certain: when stars collide, the universe puts on a show unlike anything else, and when it does, we'll be watching. If black holes are the universe's ultimate gluttons, sucking in everything that crosses their event horizons, white holes would be their polar opposites, cosmic fountains endlessly spewing out matter and energy but never swallowing a single atom. These hypothetical objects, first proposed as mathematical curiosities in Einstein's theory of relativity, are essentially black holes running backward in time. Where a black hole's gravity is so strong nothing escapes, a white hole's repulsion is so absolute nothing enters. It's the universe's ultimate one-way street flipped inside out. The idea might sound like pure science fiction, but some physicists take it seriously. White holes emerge naturally from the equations of general relativity, just like black holes did before they were discovered. In theory, if you could hit rewind on a black hole's life, you'd see it explode outward as a white hole, a process that might describe the Big Bang itself, with our universe erupting from a primordial white hole singularity. The catch: white holes violate the second law of thermodynamics, which says entropy always increases. A black hole forming a star from its own debris would be like a shattered glass reassembling itself mid-air. Yet quantum mechanics offers a loophole. Some theories suggest black holes could transition into white holes at the end of their evaporation, releasing their trapped information in a final burst. Now for the cosmic twist. Some astronomers believe we might have already spotted white holes in disguise. Certain gamma-ray bursts, the most energetic explosions in the universe, don't fit the usual mold of collapsing stars or merging neutron cells. A handful of these events, like GRB 060614, release energy in bizarrely smooth, symmetrical patterns, lacking the chaotic afterglow of traditional stellar catastrophes. Could these be white holes briefly flickering into existence, their event horizons disgorging pent-up energy before snapping shut? Skeptics point to simpler explanations. Perhaps these odd bursts come from magnetars, highly magnetized neutron stars experiencing seismic fractures. Others suggest they're the death cries of primordial black holes, vanishing in bursts of Hawking radiation. But the white hole hypothesis lingers because it challenges us to think differently about time, entropy, and the very fabric of causality. If white holes exist, even fleetingly, they'd rewrite the rules of how matter and energy flow through the cosmos. What makes this speculation so electrifying isn't just the science, it's the philosophical weight. White holes force us to confront whether the universe plays favorites with time's arrow, or if there are places where the rules reverse and creation overpowers destruction. Until we catch one in the act, they'll remain the ultimate cosmic thought experiment, less an object, more a mirror reflecting how much we still don't understand about the boundaries of reality. Galaxies are supposed to play by certain cosmic rules that dark matter has written in invisible ink across the universe. This mysterious substance acts as the scaffolding for galaxy formation, its gravity pulling stars and gas into the majestic spirals and ellipticals we see today. But in 2018, astronomers stumbled upon a cosmic anarchist NGC 1052DF2, a galaxy that refuses to follow the script. This faint, ghostly smudge of stars, located 65 million light-years away in the constellation Cetus, does the unthinkable. It appears to have almost no dark matter at all. At first glance, NGC 1052DF2 looks like any other ultra-diffuse galaxy, a wispy, see-through collection of stars so thinly spread you could fly through it for millennia and never touch a single sun. But when researchers measured the motions of its star clusters, expecting to see the telltale tug of unseen mass, they got a shock. The stars were moving sluggishly, their speeds matching only the gravity from visible matter. No hidden bulk, no dark matter halo. It was as if someone had peeled away the universe's hidden skeleton, leaving behind a galaxy that shouldn't be able to hold itself together. The discovery sent ripples through cosmology. Dark matter isn't just a minor player. It's thought to outweigh normal matter 5-1, dominating galaxy formation from the earliest moments of the universe. Without it, models suggest galaxies like NGC 1052DF2 should have long since disintegrated, their stars scattered by tidal forces or internal motions. Yet here it is, chilling in defiance, its tenuous grip on existence flouting everything we thought we knew. How did this cosmic misfit come to be? One theory suggests a violent past. Perhaps it was once a normal galaxy until a collision with a neighbor ripped away its dark matter, leaving behind a stripped skeleton of stars. Supporting this, the galaxy lies near a massive elliptical, NGC 1052, whose gravity could have played the role of cosmic thief. Others propose an even wilder idea. What if dark matter and normal matter aren't as inseparable as we thought? Could some rare quirk of physics have let this galaxy form with almost no dark matter from the start, like a lone plant sprouting in barren soil? The plot thickened with the discovery of a second dark matter-deficient galaxy, NGC 1052DF4, lurking nearby. Suddenly, this wasn't just a fluke, it was a pattern. Skeptics question the measurements, arguing that distance errors or hidden gas might explain the missing mass. But follow-up studies, including meticulous Hubble observations, only cemented the anomaly. These galaxies are real, and their defiance can't be easily dismissed. What makes NGC 1052DF2 so revolutionary isn't just its existence, it's the questions it forces us to confront. If dark matter is truly absent here, does that mean it's not as essential to galaxy formation as we believed? Or does it hint at something stranger, that dark matter can be turned off under certain conditions, like a switch flipped by environments we don't yet understand? Every observation chips away at the neat framework we've built, reminding us that the universe reserves the right to break its own rules. For now, this galactic rebel stands as a tantalizing outlier, a cosmic troublemaker challenging us to rethink the invisible forces shaping the cosmos. Whether it's a freak accident or a sign of deeper physics waiting to be uncovered, one thing's clear: the universe still has surprises up its sleeve, and sometimes they come in the form of a galaxy that forgot to bring its dark matter to the party. On October 15, 1991, a cosmic bullet tore through Earth's atmosphere with a force that shouldn't exist, streaking over Dugway Proving Ground in Utah at nearly the speed of light. This single subatomic particle, later dubbed the "Oh my God" particle, packed the kinetic energy of a baseball pitch into a space smaller than an atom. To put that in perspective, it hit with 40 million times the power of particles accelerated in the Large Hadron Collider, making it the most energetic cosmic ray ever recorded. And here's the kicker: we still have no idea what cosmic powerhouse could have launched it. Most cosmic rays are protons or atomic nuclei accelerated to high speeds by supernova or pulsars. But the "Oh my God" particle and its ultra-high energy can defy these modest origins. Their energies exceed the theoretical limit for particles accelerated within our galaxy, known as the Greisen-Zatsepin-Kuzmin cutoff. Beyond this threshold, particles should lose energy to collisions with cosmic microwave background photons long before reaching Earth. Yet these phantom bullets keep arriving, suggesting they're either born nearby, which would require undiscovered physics, or hail from extragalactic sources so violent they bend the laws of known astrophysics. The leading suspect: active galactic nuclei, where supermassive black holes spew jets of plasma capable of slingshotting particles to insane velocities. Yet even these cosmic monsters struggle to explain the "Oh my God" particle's energy without invoking exotic mechanisms, like magnetic reconnection on scales we've never observed. Another contender, gamma-ray bursts, the universe's most luminous explosions, might briefly create conditions ripe for particle acceleration beyond anything in our models. Then there's the wildcard topological defects, hypothetical relics from the early universe's phase transitions, decaying and releasing energy that makes supernova look like firecrackers. The real frustration lies in their elusiveness. Unlike gamma rays or neutrinos, ultra-high-energy cosmic rays are warped by galactic magnetic fields en route to Earth, scrambling their trajectories and hiding their birthplaces. It's like tracing a ricocheted bullet back to a sniper miles away. Observatories like the Pierre Auger Array in Argentina deploy thousands of detectors across square miles, waiting for the rare air shower these particles trigger in the atmosphere. Each detection is a breadcrumb, but the trail leads deeper into the cosmic unknown. What makes these phantom particles so electrifying isn't just their mystery, it's the doors they might unlock. If their origins lie in realms beyond standard astrophysics, they could be messengers from the universe's most extreme environments, carrying clues about quantum gravity, extra dimensions, or even the birth cries of primordial black holes. Every detection is a whisper from the void, challenging us to rethink not just how particles accelerate, but how energy itself behaves at the very edge of reality. And until we solve their riddle, they'll keep streaking through our skies, cosmic enigmas written in trails of ionized air, begging us to look up and wonder. The cosmic microwave background is often called the universe's baby picture, but in the constellation Eridanus, that snapshot holds a chilling anomaly. Stretching nearly 2 billion light-years across, the so-called Eridanus supervoid isn't just a cold patch in the CMB. It's a cosmic freezer burn, a region where temperatures dip 70 microkelvin below the surrounding average. When astronomers first spotted this aberration, it seemed like a fluke until the Planck satellite's ultra-precise measurements confirmed its reality, deepening the mystery. This isn't just a statistical blip. The odds of such an extreme temperature drop occurring randomly, less than 1 in 200,000. So what carved this icy scar into the fabric of the cosmos? One leading theory points to a void, a vast, sparsely populated bubble in the universe's structure where galaxies are eerily absent. Photons passing through such a region would lose energy as they climb out of its gravitational well, a phenomenon called the integrated Sachs-Wolf effect. But here's the catch. To explain the cold spot scale, we'd need a void 10 times larger than any ever observed. A cosmic chasm so vast it defies our understanding of how matter clusters. Surveys have found hints of underdense regions nearby, but nothing expansive enough to account for the temperature plunge. It's like finding a single footprint the size of a continent, with no giant in sight. This mismatch has sparked radical alternatives, the most tantalizing being the multiverse hypothesis. Some cosmologists suggest the cold spot could be a bruise from a collision with another universe during inflation, the universe's explosive early growth. In this scenario, our cosmic bubble might have brushed against another in a higher dimensional space, leaving behind a defect in spacetime structure. String theory permits such encounters, predicting that colliding universes could imprint irregularities in the CMB. The cold spot's sharp edges and unusual polarization patterns align suspiciously with these models, as if we're staring at a celestial fingerprint from beyond our reality. Yet skepticism remains. Critics argue that incomplete galaxy surveys or unaccounted for foreground dust might still explain the anomaly without invoking parallel universes. Others propose that cosmic textures, exotic defects in spacetime's topology from the early universe, could mimic the cold spot signature. The debate rages because the stakes are cosmic. If the multiverse interpretation holds, it wouldn't just solve a puzzle, it'd crack open a window to realms beyond our own, proving we're part of something infinitely grander. What makes the Eridanus cold spot so electrifying isn't just its existence, it's the way it taunts us with possibilities. Whether it's a void we've yet to fully map, a relic of a cosmic collision, or something beyond our current physics, one thing's clear: the universe's baby picture has a smudge we can't ignore. And somewhere in that icy silence, there might be answers waiting to redefine everything we know about existence itself. Picture this: a particle that doesn't behave like a particle at all. It carries energy, interacts with matter, yet refuses to play by the rules we've written for every other speck of existence. This is the unparticle, a theoretical wildcard that could rewrite physics as we know it. The idea was first proposed in 2007 by Harvard physicist Howard Georgi, who dared to ask, what if there's an entire sector of reality where particles don't act like discrete little balls, but instead blur into something stranger, something that defies the very definition of thingness? At its core, the unparticle hypothesis challenges one of the most basic assumptions of the Standard Model, that particles have definite masses and spins. Instead, unparticles would exist in a quantum haze, their properties smeared across a spectrum of possibilities. Imagine tossing a pebble into a pond and watching the ripples spread outward, but then realizing the pebble itself never actually existed as a solid object. That's the eerie essence of unparticles. They'd leave measurable effects, energy signatures, gravitational disturbances without ever resolving into neat, predictable forms like electrons or quarks. Where could these phantoms be hiding? The answer might lie in the universe's most extreme environments, near merging black holes or in the hearts of neutron stars, where gravity warps spacetime beyond recognition. Unparticle effects could subtly alter how matter behaves. Some theorists suggest they might even explain dark matter's elusive nature, not as weakly interacting massive particles, but as a diffuse, unparticle-like medium woven through the cosmos. The key clue: unparticles would interact with ordinary matter through forces we've never detected, leaving faint fingerprints in particle collider data or high-energy cosmic ray showers. The real magic of this idea lies in its defiance. unparticles aren't just another entry in the particle zoo. They represent a radical departure from the building block view of reality. If proven, they'd force us to grapple with a universe where the line between particle and not particle blurs, where matter can be both there and not there in ways that make quantum entanglement look straightforward. It's a reminder that for all our breakthroughs, physics might still be missing whole chapters of existence pages written in a language we're only starting to decipher. Of course, skepticism runs deep. Without direct experimental evidence, unparticles remain a tantalizing what if. Yet the very possibility excites physicists because it stretches the imagination, probing the edges of what's mathematically possible. Whether they're real or not, unparticles embody science's greatest strength, the courage to invent ideas so strange they might just be true. And somewhere between the equations and the experiments, we might yet find proof that reality is far weirder than our boldest theories dared to suggest. Imagine a world where 3 suns blaze in the sky, 2 locked in a tight orbital dance while a third wheels majestically farther out, casting shifting shadows across alien landscapes. This isn't science fiction, it's the reality of Kelt 4ab, a gas giant orbiting one star in a triple star system located 685 light-years away. Most exoplanets we've discovered cling to single stars, their orbits predictable and stable. But Kelt 4ab defies the odds, thriving in a gravitational circus where the rules of planetary survival seem rewritten nightly. The mechanics of this system are mind-bending. The primary star, Kelt 4a, hosts the planet in a relatively close orbit, so close, in fact, that a year there lasts just 3 Earth days. Meanwhile, the other 2 stars, Kelt 4b and Kelt 4c, whirl around each other like a pair of frenzied dancers before circling the main star at a distance roughly equivalent to Saturn's orbit around our Sun. From the planet's perspective, the 2 secondary stars would appear as dazzling pinpricks of light, sometimes merging into one, other times drifting apart in a slow celestial waltz. The gravitational forces at play here should by all rights have ripped Kelt 4ab apart or flung it into the void long ago. Yet somehow it persists a cosmic tightrope walker balancing against tides of chaos. How does this world endure? One theory points to its sheer heft. As a hot Jupiter, Kelt 4ab is a gas giant nearly 1.5 times the mass of our Jupiter, with gravity strong enough to anchor itself against the tugs of its stellar neighbors. But mass alone doesn't explain its resilience. Computer simulations reveal that the secret might lie in the system's architecture. The 2 outer stars orbit far enough from the planet's host star that their combined gravitational pull averages out over time, creating zones of relative stability. It's like being on a boat rocked by gentle swells rather than crashing waves, unsettling but survivable. Yet Kelt 4ab isn't the only oddball in this cosmic menagerie. Other triple-star systems like HD 131399 and GW Orionis host planets that defy expectations. GW Orionis, for instance, boasts a protoplanetary disk so warped by its 3 stars that it's berthing planets on wildly tilted orbits, like marbles rolling around a bent plate. These discoveries force astronomers to reconsider how and where planets can form. Traditional models assumed multi-star systems were too chaotic for planetary nurseries, but nature keeps proving otherwise. The implications stretch beyond curiosity. If planets can survive, even flourish, in such turbulent environments, the universe might be teeming with worlds we once thought impossible. Imagine deserts where triple sunsets paint the sky in shifting hues, or frozen plains where daylight never fades completely thanks to the eternal glow of multiple stars. For life, the challenges would be extreme: blistering radiation, wild temperature swings, and gravitational stresses that could trigger endless quakes. But if there's one lesson Kelt 4ab teaches us, it's that the cosmos thrives on defiance. Where we see chaos, nature finds a way. What's truly humbling is how much we still don't understand. Every stable planet in a multi-star system is a slap to our assumptions, a reminder that the universe's imagination outpaces our own. As telescopes grow sharper, probing deeper into these stellar tangles, who knows what other survivors will find? Worlds that shouldn't exist, orbiting stars that refuse to play by the rules. And somewhere among them, there might be a planet like no other, waiting to rewrite the story of how solar systems live and die. The vacuum of space isn't empty. Not even close. What we perceive as nothingness is actually a seething quantum froth, where particles and antiparticles flicker in and out of existence so fast they defy detection. This isn't theoretical abstraction, it's measurable reality, with consequences that ripple across the cosmos. The quantum vacuum is alive with virtual pairs, electrons and positrons, quarks and antiquarks, all dancing on the edge of reality, borrowing energy from the universe to exist for mere fractions of a nanosecond before annihilating back into the void. But here's the twist. This ephemeral chaos might hold the keys to understanding why the universe is flying apart faster than anyone predicted. The phenomenon known as vacuum polarization isn't just a quirky quantum side effect. In strong electromagnetic fields, like those near neutron stars or black holes, these virtual particles can become real, ripped apart before they can annihilate. The result, a plasma of matter and antimatter crackling through what we thought was empty space. Astronomers have glimpsed hints of this in the magnetospheres of pulsars, where vacuum polarization is thought to distort light in ways classical physics can't explain. But the implications stretch far beyond stellar oddities. If the quantum vacuum isn't passive, if it actively resists or amplifies the expansion of spacetime itself, we might be staring at a solution to the dark energy puzzle. Einstein's cosmological constant, that infamous blunder he inserted into his equations to keep the universe static, has found new life as a candidate for dark energy. But there's a glaring mismatch. Quantum field theory predicts the vacuum should buzz with an energy density a staggering 120 orders of magnitude stronger than what we observe. This isn't just a rounding error, it's the worst prediction in physics. Some theorists argue the answer lies in the vacuum's ability to self-regulate, cancelling out its own energy through symmetries we don't yet understand. Others propose wilder ideas. What if dark energy isn't constant at all, but the leftover echo of primordial vacuum fluctuations frozen into the fabric of spacetime during inflation? Then there's the Casimir effect, an eerie demonstration of the quantum vacuum's power. Place two uncharged metal plates impossibly close together in a vacuum, and they're pushed together by nothing more than the pressure of virtual particles outside the gap. It's as if the universe itself is squeezing them, a force born from the absence of particles rather than their presence. If empty space can exert pressure, could it also drive expansion on cosmological scales? The math suggests yes, but with a twist. The vacuum's energy density should decelerate expansion, not accelerate it. This contradiction has led to radical rethinking. Perhaps the quantum vacuum decays over time, or interacts with dark matter in ways that flip its effects. The most tantalizing possibility, that we're seeing the fingerprints of extra dimensions. In string theory, the quantum vacuum isn't confined to our familiar 3 dimensions of space. It vibrates through higher dimensional realms we can't perceive. Energy leaking into or out of these dimensions could explain why the vacuum's observed strength is so weak compared to predictions. It's a cosmic sleight of hand, with the missing energy hidden in folds of reality we've yet to map. What makes the quantum vacuum so electrifying isn't just its mysteries, it's the way they force us to confront the limits of our theories. Here's a phenomenon that links the infinitesimal world of particle physics to the vastness of cosmic expansion, a bridge between quantum mechanics and general relativity. Every unanswered question, from the cosmological constant problem to the nature of dark energy, is a reminder that the universe's greatest secrets might be hiding in plain sight, woven into the very fabric of nothingness itself. And somewhere in that seething virtual sea, there might be clues waiting to rewrite our understanding of everything. Neutron stars are cosmic extremes, stellar corpses so dense that a single teaspoon of their material would weigh billions of tons on Earth. Their surfaces are polished smoother than any mirror by gravity's unrelenting crush, with imperfections no taller than a grain of sand. At least that's what we used to think. Recent simulations reveal something astonishing. Even these perfect spheres might hide tiny mountains, wrinkles in space-time barely a millimeter high, yet massive enough to send ripples through the fabric of the universe. The physics behind these minuscule mountains bends the imagination. A neutron star's crust isn't like Earth's rocky shell. It's a lattice of atomic nuclei packed so tightly they form a crystalline structure harder than diamond. When magnetic fields or internal stresses warp this crust, the resulting deformations create hills so small you could step over them, but with bases spanning miles. What makes them extraordinary isn't their height, it's their mass. Because neutron star material is absurdly dense, even microscopic bumps weigh more than entire mountain ranges on Earth. That sheer heft warps spacetime around them, creating gravitational distortions detectable across interstellar distances. These spacetime ripples could solve a long-standing mystery: why some neutron stars, like the famous Pulsar J 1023+0038, emit periodic gravitational waves. Traditional models assumed only cataclysmic events like collisions could produce such signals, but millimeter-scale mountains might generate them continuously as the star spins. Picture a lighthouse beam, but instead of light, it's broadcasting gravitational tremors with each rotation, a whisper of spacetime itself being stretched and compressed. The real magic lies in what these mountains reveal about neutron star interiors. By studying their formation, physicists can probe the bizarre states of matter lurking beneath the surface. At certain depths, pressures might crush nuclei into a quantum soup of quarks, or even stranger phases like nuclear pasta, structures resembling spaghetti or lasagna sheets, sculpted by competing forces. Each tiny surface bump is a clue, a fingerprint of the star's hidden layers. Yet detecting these features pushes our technology to the limit. Current gravitational wave observatories like LIGO aren't sensitive enough to spot the subtle signals from rotating mountains, but next-generation tools like the Einstein telescope or space-based LISA might catch them. It's a tantalizing prospect, using spacetime itself as a microscope to study topography on objects thousands of light-years away. What's most humbling isn't the scale of these mountains, it's the scale of their implications. In a universe where black holes dominate headlines, neutron stars remind us that even the tiniest imperfections can ripple across reality, bending the rules of physics in ways we're only beginning to understand. And somewhere in those millimeter-high peaks, there might be answers to questions we haven't even thought to ask yet. The James Webb Space Telescope was supposed to clarify the universe's origins, not throw them into chaos. Yet that's precisely what happened when it peered back toward cosmic dawn and spotted galaxies so massive, so mature they shouldn't exist. These cosmic giants, like the 4 billion solar mass behemoth nicknamed the Sparkler, were caught on camera as they appeared just 300 to 400 million years after the Big Bang. That's barely 2% of the universe's current age, a time when models predicted only frail, infant galaxies could form. Instead, JWST found sprawling cities of stars already polished with ancient stellar populations and complex structures. It's like stumbling upon a skyscraper in the ruins of a prehistoric village, an architectural marvel where only mud huts should stand. What makes these galaxies so baffling isn't just their size, it's their composition. Spectroscopy reveals heavy elements like oxygen and neon, forged in the hearts of stars and scattered by supernova. But creating such abundances requires multiple generations of stars living, dying, and recycling their material over billions of years. Yet here they are, glittering in the universe's infancy, as if cosmic evolution hit fast forward. One leading theory suggests these galaxies formed from ultra-dense pockets of primordial gas, collapsing under their own weight far faster than modern star-forming regions. Another radical idea posits that the early universe's dark matter, which provides the gravitational scaffolding for galaxies, might have clumped more efficiently than we thought, jump-starting growth before the cosmos had time to blink. But even these explanations strain credibility. Simulations of cosmic dawn struggle to produce galaxies this massive without invoking physics beyond our standard models. Some theorists wonder if we're seeing evidence of exotic phenomena like primordial black holes seeding early structure, or even remnants of a previous cosmological cycle. A speculative idea called conformal cyclic cosmology, where the Big Bang wasn't the beginning but a reboot. Others suggest the telescope might be playing tricks on us. Gravitational lensing from unseen mass could be magnifying smaller galaxies, making them appear older and more developed than they truly are. Yet follow-up observations have only deepened the mystery, with JWST finding dozens more of these rule breakers lurking in the deep field images. The implications are staggering. If galaxies could form this rapidly, our entire timeline of cosmic evolution might need rewriting. Perhaps dark energy's influence has changed over time or inflation. The universe's explosive early growth unfolded differently than we assumed. Or maybe, just maybe, we're glimpsing a universe where the rules themselves were different in those first fiery moments. A realm where matter behaved in ways no lab or equation can replicate. Every new JWST discovery chips away at the foundations of cosmology, leaving us to wonder how much of what we think we know is just the tip of a far stranger iceberg. What makes this puzzle so exhilarating isn't just the science, it's the humility it demands. For centuries, we've mapped the cosmos assuming it unfolded in predictable stages. Now, with a single telescope, the universe has handed us a cosmic curveball, a reminder that the past might be wilder than we ever dared imagine. Whether these galaxies force us to revise our models or rewrite them entirely, one thing's certain: the story of how everything began just got a lot more interesting. And somewhere in that ancient starlight, there might be clues waiting to unravel the very nature of time itself. The universe isn't just a scattering of galaxies, it's a vast, intricate web, with threads of gas and dark matter weaving everything together into a tapestry of unimaginable scale. For decades, this cosmic web existed mostly in theory, its delicate filaments too faint to detect. But now, cutting-edge telescopes are finally pulling back the veil, revealing wispy tendrils of gas stretching between galaxy clusters like invisible bridges. These filaments, long considered the missing link in our understanding of cosmic structure, aren't just proving the web exists, they're reshaping how we see the universe's skeleton. The challenge has always been visibility. The gas in these filaments is so hot millions of degrees it doesn't emit visible light. Instead, it glows faintly in X-rays, a whisper against the cosmic background. To spot them, astronomers turn to a clever trick, using the light of distant quasars, the brilliant cores of active galaxies, as cosmic flashlights. As this light travels through the web, certain wavelengths get absorbed by ionized oxygen and hydrogen in the filaments, leaving telltale dips in the quasar spectrum. It's like finding smoke by watching how it dims a far-off lantern. The European Space Agency's XMM Newton telescope and Japan's Hitomi satellite have both caught these fingerprints, confirming that the web isn't just theoretical scaffolding, it's real and it's teeming with matter. But the real breakthrough came with the discovery of a filament stretching between two galaxy clusters, Able 399 and Able 401, about 1 billion light-years away. This thread of gas, detected by the Planck satellite and later studied in detail by the Atacama Large Millimeter Array, is a monster 50 million light-years long, with temperatures soaring to 80 million degrees. What's astonishing isn't just its scale, but its role. These filaments are cosmic highways, funneling gas into clusters and fueling the birth of new stars. Without them, galaxies would starve, cut off from the raw material that keeps them alive. Yet even now, the web remains elusive. Its filaments are so diffuse that mapping them feels like tracing the outline of a shadow. Some theorists suggest we're only seeing the densest strands, that the true web is far more intricate, with finer threads branching like capillaries. Others wonder if dark matter's grip is sculpting these filaments in ways we don't yet understand, shaping the flow of gas with invisible hands. As new telescopes like the upcoming Athena X-ray Observatory come online, we'll finally peer deeper into this hidden architecture, uncovering how the universe stitches itself together. What makes the cosmic web so mesmerizing isn't just its grandeur, it's the reminder that we're not just observers of the universe but part of its fabric. Every atom in our bodies was once scattered across these filaments, drawn into galaxies by gravity's pull. The web isn't just out there, it's in us, a silent thread connecting the cosmos to the very stuff of life. And as we trace its strands, we're not just mapping the universe, we're finding our place within it. Imagine spinning hundreds of top-of-the-line telescopes across a continent separated by thousands of miles, never touching, never communicating, and discovering they're all pointing in the same direction. That's essentially what astronomers found when they mapped the spin axes of quasars, the universe's most luminous objects, and realized something impossible. These cosmic beacons, scattered across billions of light-years, aren't oriented randomly. Their rotation axes align with one another like compass needles, all pointing north, as if some unseen hand had reached across the cosmos and set them spinning in unison. Quasars are no ordinary light sources. These are the blazing cores of distant galaxies, powered by supermassive black holes gorging on gas and stars. Each one outshines its entire host galaxy by 1,000 times, visible across the observable universe. Their spin axes should, theoretically, point in every conceivable direction, a chaotic jumble reflecting the turbulence of their birth environments. Yet when researchers analyzed data from the Sloan Digital Sky Survey, studying 93 quasars at distances up to 12 billion light-years, they found a spine-chilling pattern. The axes weren't just aligned locally, they traced a vast cosmic grid with correlations stretching farther than any known structure should permit. The scale of this alignment defies every model of cosmic evolution. Structures that large shouldn't exist under the cosmological principle, the bedrock idea that the universe is uniform on grand scales. Yet here's the evidence etched in light. Quasars separated by distances so vast that light hasn't had time to travel between them since the Big Bang, somehow synchronized. It's as if the universe's largest structures are dancing to a tune we can't hear, their motions choreographed by forces beyond our current physics. So what could orchestrate such a phenomenon? One radical theory points to primordial magnetic fields, cosmic-scale magnetism woven into the fabric of spacetime during inflation, the universe's explosive infancy. These fields, stretching across unfathomable distances, might have imprinted a preferred direction on the swirling gas that formed quasars, like a cosmic wind aligning weather vanes. Others propose an even wilder idea, that the alignment reflects the universe's large-scale topology, hints of a repeating structure or symmetry hidden in the geometry of spacetime itself. Some string theory models, for instance, suggest our universe might be a brane floating in higher dimensional space, its quirks reflecting unseen dimensions. Then there's the unsettling possibility that we're seeing the ghostly influence of something outside our observable universe. Just as the moon's gravity tugs on Earth's oceans, a neighboring universe, or some other exotic structure beyond our cosmic horizon, might be exerting a subtle torque on the fabric of reality, nudging quasars into alignment over eons. It's a notion that borders on metaphysics, yet the data refuses to let it go. Of course, skepticism lingers. Could this be a statistical fluke, a trick of observational bias? Teams have run the numbers, accounting for selection effects and measurement errors, and the signal persists. Others suggest that quasars might preferentially form along the cosmic web's densest filaments, their spins dictated by the flow of gas into these primordial channels. But even this explanation strains to account for the alignment's sheer scale and coherence. What makes this discovery so profound isn't just the mystery, it's the implications. If quasars can align across billions of light years, what else might be connected in ways we've yet to imagine? Are we glimpsing a deeper layer of cosmic order, a hidden architecture that binds the universe together? Or is this a clue that the randomness we've long assumed is fundamental might be an illusion, a veil hiding a far more intricate design? Every new survey, every sharper telescope brings us closer to answers, or perhaps to questions we've not yet dared to ask. Black holes were supposed to be the ultimate rebuke to simplicity, cosmic monsters born from the chaotic collapse of massive stars, each one a unique fingerprint of violence and history. Yet in the 1960s, physicist John Wheeler coined a phrase that turned this assumption on its head. Black holes have no hair. Not literal hair, of course, but a metaphor for the startling idea that these gravitational beasts might be disturbingly simple. No matter how complex the star that birthed them, no matter what planets, gas, or light they've devoured since, all black holes could be fundamentally identical, defined by just three numbers: mass, spin, and electric charge. This became known as the no-hair theorem, and it's one of the most elegant and unsettling ideas in modern physics. Think of it like this: toss a grand piano, a library of books, and a bucket of paint into a black hole, and the only traces left would be how much heavier it got, how much faster it's spinning, and whether its charge shifted slightly. Everything else, the piano's shape, the words in the books, the color of the paint, would be irretrievably erased. This isn't just a quirk of gravity, it's a radical violation of our everyday intuition. On Earth, objects carry echoes of their past. A dented car fender tells a story, a weathered book reveals its age. But black holes, they're cosmic amnesiacs, swallowing history whole and leaving no fingerprints behind. The implications ripple far beyond astrophysics. If the no-hair theorem holds, it suggests black holes are the universe's ultimate simplifiers, reducing infinite complexity to a handful of digits. This aligns eerily well with thermodynamics, where black holes behave like perfect blackbodies, absorbing all incident energy and emitting radiation with no distinguishing features beyond temperature. Even Hawking radiation, the faint glow predicted to escape black holes as they evaporate, carries no information about what fell in, at least according to early calculations. That's what made the information paradox so explosive. If black holes destroy information, they violate quantum mechanics' sacred law that information must always be preserved. But here's where things get messy. Recent advances in string theory and quantum gravity hint that black holes might have soft hair, subtle, low-energy imprints on their event horizons that encode fragments of what's fallen inside. These wouldn't be the messy, detailed hair Wheeler dismissed, but more like faint quantum whispers, patterns in the fabric of space-time itself. Imagine dipping your finger into water and withdrawing it. The ripples that remain aren't your fingerprint, but they're not entirely random either. Similarly, black holes might retain ultra-faint traces of their meals, not enough to rebuild a swallowed star, but enough to satisfy quantum physics' demand for information conservation. The debate rages because the stakes are cosmic. If black holes truly are bald, it means the universe has a built-in eraser, a way to permanently destroy the very information that makes reality coherent. If they have soft hair, it hints at a deeper layer of quantum structure woven into space-time, a ledger keeping track of everything that's ever crossed the event horizon. Gravitational wave observatories like LIGO might settle the question by analyzing the ring-down of merging black holes, the final wobbles as they settle into a new, unified form. Any deviations from the no-hair theorem's predictions could reveal hidden complexities, flaws in our understanding of how gravity and quantum mechanics intertwine. What makes the no-hair theorem so captivating isn't just the physics, it's the philosophy. In a universe that thrives on complexity, black holes stand as enigmatic minimalists, reducing the rich tapestry of existence to 3 bare numbers. Whether they're truly bald or just hiding their secrets in quantum frizz, one thing's certain: these cosmic paradoxes will keep challenging us, pushing the boundaries of what we think we know about information, entropy, and the very nature of reality itself. The universe is expanding, that much we know, but how fast it's expanding has become one of the most heated debates in modern cosmology. On one side, we have the Hubble constant, calculated by observing nearby galaxies and the afterglow of the Big Bang. On the other, measurements of distant supernova and gravitational lensing. The problem: these two methods keep giving us different answers so stubbornly inconsistent that astronomers call it the Hubble tension. And this isn't just a minor discrepancy. We're talking about a gap significant enough to suggest we might be missing something fundamental about how the cosmos works. Take the cosmic microwave background, for example. By studying the faint whispers of radiation left over from the universe's infancy, the Planck satellite delivered a Hubble constant of roughly 67 kilometers per second per megaparsec. That's how fast space itself stretches over distance. But then came the supernova measurements, exploding stars so bright we can see them across billions of light years. These standard candles pointed to a much faster expansion, 73 kilometers per second per megaparsec. At first, scientists brushed it off as measurement errors. But the gap persisted even as methods improved. Now, with James Webb's razor-sharp infrared eyes confirming the supernova data, the tension has snapped from curiosity to crisis. So why does this matter? Because the expansion rate isn't just a number, it's a cornerstone of cosmology. It tells us the universe's age, its fate, even the nature of dark energy. If our measurements disagree, it's like building a bridge where one side insists the river is a mile wide and the other swears it's only half that. Something has to give. One possibility: dark energy isn't constant as we've assumed, but evolves over time, accelerating the universe in fits and starts. Another wild card: what if there's an unknown particle, a dark radiation, subtly tweaking the early universe's physics? Then there's the nuclear option. Maybe we've misunderstood gravity itself. Modified Newtonian dynamics, or MUND, suggests gravity behaves differently on cosmic scales, which could throw off our expansion calculations. It's a radical idea, but when the data refuses to cooperate, radical ideas start looking less like fringe theories and more like necessary correctives. Whatever the answer, the Hubble tension isn't just a puzzle, it's an invitation. An invitation to rethink, to explore, to admit that the universe might still be holding its greatest secrets close, waiting for us to ask the right questions. And until we do, every conflicting measurement is a reminder: the cosmos doesn't owe us clarity, we have to earn it. Moons are supposed to be small, at least that's what our solar system taught us. From Earth's modest companion to Jupiter's swarm of rocky satellites, moons typically pale in comparison to their host planets. But in the distant Kepler 1625 system, astronomers may have stumbled upon a cosmic oddity that flips this expectation on its head. A potential moon so colossal it rivals the size of Neptune, dwarfing every known satellite in our celestial neighborhood. This isn't just a moon, it's a behemoth, a gravitational puzzle that challenges everything we thought we knew about how moons form and survive. The story begins with Kepler 1625b, a gas giant orbiting a sun-like star 8,000 light-years away. When researchers noticed peculiar dips in the planet's transit, light curves, subtle, irregular dimming patterns that couldn't be explained by the planet alone, a tantalizing possibility emerged. What if this wobble in the data wasn't caused by another planet, but by an unseen moon? further analysis revealed a second, smaller dip in starlight trailing the main transit, like a shadow following its master. The numbers were staggering. This moon candidate, dubbed Kepler 1625b, appeared to be nearly 3% the mass of its host planet. To put that in perspective, our moon is just 1% the mass of Earth. This thing wasn't a moon, it was a near twin, a planetary scale companion locked in an unlikely gravitational embrace. Theories scrambled to explain how such a monstrosity could exist. Traditional moon formation models offer few answers. Moons typically arise in one of three ways: coalescing from debris rings after planet formation like Saturn's moons, being captured by a planet's gravity like Neptune's Triton, or forming through giant impacts like Earth's moon. But none of these easily account for Kepler 1625b's absurd proportions. A collision massive enough to spawn a Neptune-sized moon would likely obliterate both bodies. Capture seems equally improbable. Snagging an object that large would require freakish precision, like threading a cosmic needle. Even the disk theory falters. Protoplanetary disks rarely contain enough material to forge a moon of this scale. Then there's the orbital mystery. Kepler 1625b orbits unusually far from its host, about 20 planetary radii away, compared to our moon's 30 Earth radii. At that distance, the moon should be vulnerable to gravitational perturbations, either drifting away or being torn apart by tidal forces. Yet here it is, stubbornly persisting in a configuration that defies stability calculations. Some astronomers wonder if we're seeing a rare binary planet system mislabeled as a moon, a pair of worlds born together from a shared gas disk. Others suggest a more dramatic history. Perhaps this moon was once a free-floating planet, captured during a chaotic early epoch when the Kepler 1625 system was still settling into its current arrangement. The debate rages because the stakes are high. Confirming Kepler 1625b would force a rewrite of astrophysics textbooks, proving that moons can grow to planetary scales under the right conditions. It would also open new avenues for exomoon hunting, suggesting that previous searchers might have overlooked giants hiding in plain sight. Future telescopes like the James Webb Space Telescope could settle the controversy by scrutinizing the system for atmospheric signatures or gravitational wobbles. Until then, this enigmatic candidate lingers at the edge of discovery, a cosmic question mark reminding us that the universe thrives on defying expectations. Whether it's a moon, a planet, or something in between, one thing's certain: the rules of celestial companionship are far stranger than we ever imagined. Imagine stumbling upon a time capsule buried for billions of years, a relic so perfectly preserved it transports you back to the dawn of existence. That's precisely what astronomers found hiding in plain sight: fossil clouds, vast reservoirs of primordial gas drifting through the modern universe like cosmic ghosts. These ancient pockets of matter have remained chemically untouched since the Big Bang, never forged into stars, never polluted by the ash of supernova. They're the universe's ultimate purists, rejecting the chaos of stellar evolution to cling stubbornly to their original state. What makes these clouds so extraordinary is their purity. The early universe was a far simpler place: just hydrogen, helium, and trace amounts of lithium, the only elements cooked up in the first minutes after the Big Bang. Everything heavier, from the oxygen we breathe to the iron in our blood, was forged later in the hearts of stars and scattered across the cosmos by their explosive deaths. Most gas in the modern universe bears the fingerprints of this stellar recycling, laced with metals, as astronomers call any element heavier than helium. But fossil clouds, they're the last holdouts, with metal abundances 100,000 times lower than our sun's. It's like finding a drop of seawater untouched by salt in the middle of the ocean. The first confirmed fossil cloud was discovered in 2011, lurking in the distant constellation Ursa Major. Using the Keck Observatory in Hawaii, researchers spotted its telltale signature in the spectrum of a quasar, the brilliant beacon of a supermassive black hole. As the quasar's light passed through the cloud, specific wavelengths were absorbed by its pristine gas, revealing an elemental composition straight out of the cosmos's infancy. Since then, a handful of others have been found, each one a cosmic time machine offering an unfiltered glimpse of the universe before stars existed. But here's the puzzle. How did these clouds survive 13.8 billion years of cosmic evolution unscathed? In a universe where galaxies collide, stars explode, and black holes churn the interstellar medium into a chemical soup, their survival defies the odds. One theory suggests they've been hiding in the cosmic web's loneliest strands, vast, thread-like structures of gas where gravity hasn't yet triggered star formation. Another proposes they're refugees from dark galaxies, dwarf systems so star-poor they're nearly invisible, their gas reservoirs left unmined. The hunt for these relics isn't just academic, it's a direct line to understanding how the universe transitioned from simplicity to complexity. By studying them, we're essentially peering at the raw ingredients of creation, the pristine matter that would one day ignite into the first stars. And with next-generation telescopes like the Extremely Large Telescope coming online, we're on the verge of finding more, each one a silent witness to the cosmos's untouched youth, waiting to whisper its secrets across the eons. Einstein famously called it spooky action at a distance, a phrase dripping with skepticism about the bizarre behavior of quantum particles. Yet today, experiments across the globe confirm that entanglement, this spooky phenomenon, is very real, and it defies everything we thought we knew about how the universe communicates. Picture two electrons born from the same quantum event, whisked light years apart. Measure one's spin, and its partner instantly snaps into the opposite state, no matter how vast the separation. Not at the speed of light, not after a delay, instantly. It's as if space and time don't exist for these particles, a cosmic loophole that left Einstein so unsettled he spent years trying to disprove it. The first definitive proof came in the 1980s with Alain Aspect's groundbreaking experiments. By measuring entangled photons with carefully calibrated detectors, his team showed their correlations couldn't be explained by any hidden variables, secret codes predetermining their states. The particles were genuinely influencing each other across distances, violating the classical notion that nothing travels faster than light. Later, Anton Zeilinger's group took this further, entangling particles across the Danube River, then across continents, even between Earth and satellites in orbit. Each time the results held, entangled particles danced in perfect, inexplicable sync. But here's where it gets cosmic. In 2017, Chinese scientists used the Misha satellite to entangle photons over 1,200 kilometers, a distance so vast that any signal between them would need 4 milliseconds to traverse space at light speed. Yet when measurements were taken, the correlation was instantaneous. This wasn't just a lab curiosity, it was a universe-scale defiance of locality, the principle that objects are only influenced by their immediate surroundings. Entanglement suggests the cosmos might be threaded with invisible connections, a hidden web of relationships operating beneath the fabric of space-time. What makes this so revolutionary isn't just the physics, it's the philosophical quake it triggers. If entangled particles ignore distance, could the universe be fundamentally non-local, with everything secretly linked in ways we can't perceive? Some interpretations of quantum mechanics, like Bohmian pilot wave theory, embrace this idea, proposing a deeper layer of reality where separation is an illusion. Others argue it's a sign we're missing something profound about spacetime itself. Perhaps it emerges from something more fundamental, like a quantum network. Yet for all its mystery, entanglement isn't magic. It can't send messages faster than light. The correlations only appear random until compared, but it's already powering real-world tech like quantum encryption and computing. And as telescopes grow more sophisticated, some theorists wonder if entanglement might even leave traces in the cosmic microwave background, subtle fingerprints of the universe's earliest quantum bonds. One thing's certain, this spookiness is here to stay, a reminder that the universe's deepest truths often lurk in the spaces between what we think we know. Elon Musk didn't originate the idea that our universe might be an elaborate simulation, but he certainly thrust it into the mainstream. The billionaires claim that there's a 1 in billions chance we're living in base reality ignited fierce debate, merging ancient philosophy with cutting-edge physics. At its core, the simulation hypothesis suggests that everything we perceive, the stars, our bodies, even the passage of time, could be lines of code in some unfathomably advanced civilization's quantum computer. It's a dizzying thought, but not without its echoes in science. Quantum mechanics already shows us that particles exist in probabilistic states until observed, as if rendering only what's necessary, like a video game optimizing graphics to save processing power. Then there are the so-called glitches. Déjà vu, that eerie sense of reliving a moment, feels uncannily like a buffer reloading. The Mandela effect, where large groups misremember events. Did the Berenstain Bears always have an A? Could be chalked up to faulty memory or a patch update tweaking the simulation's historical data. Even the universe's pixelated nature hints at something artificial. At the Planck scale, spacetime isn't smooth but granular, a mesh of tiny units resembling the pixels on a screen. Some theorists argue this isn't just an analogy, it's evidence. If you zoom in far enough on a digital image, you hit pixels, zoom in on reality, and you hit Planck length. Coincidence, but the simulation argument isn't just sci-fi speculation. Oxford philosopher Nick Bostrom formalized it in a seminal 2003 paper outlining a trilemma. Either civilizations inevitably self-destruct before reaching posthuman status, they lose interest in creating ancestor simulations, or we're almost certainly living in one. The logic rests on probability. If advanced civilizations exist and they run countless simulations of their ancestors, the number of simulated minds would dwarf biological ones. Statistically, you're more likely to be one of the simulated. Critics, though, aren't convinced. They point out that simulating every particle in a universe would require energy exceeding the cosmos itself, a cosmic catch-22. Others argue the hypothesis is unfalsifiable. If glitches can be explained naturally and the simulation is flawless by design, how could we ever prove it? Even Musk's 1 in billions odds rely on shaky assumptions. What if creating conscious simulations is ethically abhorrent to advanced beings or physically impossible? Yet the hypothesis lingers because it refracts existential questions through a modern lens. If we're in a simulation, does free will exist, or are we NPCs following scripts? Are the laws of physics just user settings? And if we one day create simulations indistinguishable from reality, as some AI researchers believe possible, does that cement our place as creators or creations? There are no tidy answers, only the thrill of the question. Whether cosmic truth or provocative thought experiment, the simulation hypothesis forces us to confront the deepest mystery of all. Not just how the universe works, but what it even is. From vanishing stars to rogue black holes trailing starlight, from galactic superwaves to whispers of parallel universes, each of these 50 cosmic enigmas is a humbling reminder of how much we don't know. The universe isn't just stranger than we imagine. It's stranger than we can imagine, constantly rewriting the rules as we reach for understanding. Think about that. Even with telescopes piercing the depths of space and supercomputers simulating the birth of galaxies, the cosmos keeps its most profound secrets locked away, revealing just enough to keep us hungry for more. But here's the thrilling part: we're on the verge of cracking some of these mysteries wide open. NASA James Webb Space Telescope is peering into stellar nurseries where no human eye has seen before, while the Vera Rubin Observatory's sky scans might finally unmask the true nature of dark matter. The European Space Agency's LISA mission will listen for gravitational waves from colliding supermassive black holes, and private ventures like Breakthrough Starshot aim to send probes to Alpha Centauri within our lifetimes. Every mission, every observation is a step toward turning today's speculation into tomorrow's textbooks. So what's your cosmic obsession? Is it the eerie silence that followed the WOW signal, the hexagonal storms raging on Saturn, or the phantom galaxies that vanished without a trace? Maybe you're captivated by the idea of white holes, black holes running backward in time, or the chilling possibility that we're living in an advanced civilization simulation. Whatever it is, let that curiosity burn. Share your favorite mystery in the comments, debate the wildest theories, and keep looking up, because the universe isn't just a static backdrop to our lives, it's an ever-unfolding story, and we're all part of the audience, front row witnesses to the greatest show in existence. The best part, this list of 50 is just the beginning. For every mystery we solve, a dozen more emerge, each one a doorway to questions we haven't even thought to ask yet. So stay restless, stay questioning, and remember, the day we stop being awestruck by the cosmos is the day we stop truly seeing it. The universe is out there waiting, and the next great discovery might be just one of